Good morning, guys. Audio good, video good. Can anyone confirm if audio and video is good? Okay. Srijit, thanks for that. So, somebody, Anish, you are asking, will we solve the last year PYQ in the next half? All the PYQs have been solved as we went along the way. If you see all the questions that we have done, they are primarily from the PYQs only. And of course, I've taken something from GATE, something from other universities, and the aggregated bunch is that what the PDF that you saw that we covered from day before till now. And today also we will be covering the PYQs of graphs, hash, etc. So as we go along for every topic, I have been covering the PYQs. So we are not going to cover the PYQs again separately because it's going to be a repetition of what we already did. So Anish, I hope that clarifies. Okay, so today appears to be poorer than yesterday. Only 11 of you are here. Good morning all. Good morning, good morning. Good morning, Samiran. How many are here? 925. Okay. 925. Streamlab sets 18. Okay. Okay, couple of more minutes. Let's see how many of you are here. 40. Good morning all, good morning all. I'm just waiting for more of you to join. There are 40 of you now. Let's give it one more minute. Okay, so we'll get started. Thanks for joining last but one session. And Abhishek, I will provide the OneNote PDF after the session. It will be a OneDrive link, so you can access that at any point in time. So we will do that. Now, today, some quick announcements before we start. One is that, let me put one more reminder on the WhatsApp and then I'll start. Okay, so the reminders, the announcement that I wanted to talk about is two, three things. First is the entire series that I planned out was on the basis of not being very theoretical in nature, trying to figure out what kind of questions come and trying to align whatever I teach basis the questions that are being coming. And that's how the entire PDF, the entire PPTs that you will see have been structured, that you have been seeing, have been delivered to you. So one point is that whatever examples we have taken, they are not my manufactured examples. Some of them are, yes, I've manufactured some examples, but like 10%. 90% of the examples are from your PYQs. 90% of the examples are also some things that I have taken from GATE, and I have also taken something from relevant other universities, the top universities, right, where there were uniqueness that I saw. So it's a nutshell. Whatever examples if we see, if you do all those example topics, right, you cannot expect anything beyond that. So that's why I think it's more of a comprehensive 24-hour package deal to you, which will help you to solve any kind of problem that you come along the way. Now today, what we have planned, second announcement that I wanted to do is, today what we have planned is that the first half we will complete whatever is left. And when I was doing the first half planning for today, I found that there is a very heavyweight item in terms of sorting, right? So the sorting, if you see, there are some 6-7 sorts along with comparisons of their complexities. Now that itself becomes a very hungry in terms of time kind of a exercise, where we will need to probably talk about all the kinds of sorting, how they are done, the algorithms of them, and then talk about why the complexities are in that manner. That is derivation of complexities, not just announcing the complexities. So it's easily a 3-hour affair, right? So we could have done it in the second half, but I wanted to keep something open for you, so that you can ask me your doubts and I can push those doubts back to you. Sorting, what I'm announcing now is that later on the same WhatsApp channel that you are here in, we will not close the channel, we will keep it alive, and we will say that from a sorting perspective, a 3-hour session, dedicated session, will be conducted sometime next week. I will announce that probably by Saturday or Sunday. Basically I would choose Sunday for that matter. And that 3-hour session, I can then do proper justice to sorting. Otherwise it would be a very hurried affair. So that's something that I wanted to announce, that sorting we will not talk about it today. We will talk about it on the next session, which would be a 3-hour session, which we will do this. So net we are extending our sessions by 3 hours just to accommodate and do justice to sorting. So that's the second announcement. And the third announcement is, I have seen your, some of you have given whatever you wanted to give in terms of questions, right? And in that, whatever I have seen, whatever uniqueness I have seen, I have put it in the schedule also, right? If you see the WhatsApp, I have put those topics in the schedule where you wanted to do, let's say, Tower of Hanoi. You wanted to do a revision of BB plus tree. You wanted to do a revision of AVL. So those are the prime topics I can remember. We will go through the questions. I will open up the form for you and you can see what all questions have come. So mostly the new topic is Tower of Hanoi. Otherwise, whatever has come in is on BB plus tree. 2-3 people have written that BB plus tree, they want to do it again. So we will do B plus tree again. We will do AVL tree. We will do Tower of Hanoi. These 4 topics are confirmed in the second half. Now, if at all you have any other things, then let me know. If it is a part of my slide pack that you have already gone through, it's just a revision of what we have already gone through, I can do it. If it's not, then as I said, I will not have any slides prepared. It will be a very ad hoc lecture. So we'll figure that out. But I will go through all the questions at 2 p.m. today, and then those questions we will go through one at a time between 2 to 6. That's on the announcements. Now, I hope everybody is in line with what we are discussing, and with that standpoint, let me start off today's discussion. The sequence of today's discussion would be hashing. It's going to be a smaller topic. Then we'll do a quiz. Then we will do graphs, relatively large topic, around 1 hour it will take. So that also we will do a quiz. And then it's going to be interesting in terms of the heap, right? So heap is going to be interesting because we will work, because hashing and graph does not have much of workings, right? Graphs has some of it in terms of DFS and BFS, but in hashing, in hashing there is not much of working. It's mostly theoretical concepts. Graphs has some amount of practical concepts on DFS, BFS. But the most exciting thing that you will see, most interesting thing that you will see is on heap, where we will do a lot of workings, right? At least 3-4 problems we will solve, and we will make you understand what is heap, what is heap sort, what is max heap, what is mean heap. So that part I'm actually budgeting for around 1.5 hours. So that way we can do proper justice to things that are of high weightage. So from hashing, graph and heap, you can at least expect around 15 to 20 marks. That's my common belief. And then around 10 marks from sorting. So that way this module itself fetches you around 30 marks. That's why I was saying, I've been harping all the way that you have a lot of what do I say, interest level that you need to grow on this particular module, right? So that's something that I will say. Okay, I'm seeing Ashmita is saying audio muffled for everyone. Okay, so Ashmita, your network problem probably, because SketchUp Night is confirming it is fine. So I'll move on just for the sake of time. We start today's session with hashing. So from a hashing perspective, I just had some time to prepare these notes, not in the way that we have been doing the marathon. So for hashing and graph, it's going to be a different style of notes that you will get, but it will be in the same PDF of OneNote, right? So you will get the same OneNote link. So don't worry about that. Now, what is hashing and hash tables? The problem is that when we, let's take this example, right? We will take this classical example. We are trying to search for 90 in this entire array, right? If I search for 90 in this entire array, what is my worst case complexity? It can be order of n, right? It will be order of n, not can, it will be order of n, because this 90 could have been anywhere, right? It could have been here also. So the worst case can be order of n. So it's a waste of, when you search for some data which should appear quickly, it's a waste of time. Have you searched for, let's say in Google Maps, have you searched for an address and you see like 0.3 seconds it comes up? Does it do an array traversal to get to that particular address? It doesn't do an array traversal. It's called direct addressing. So that is the key element that you need to think, that why hashing it exists. Now hashing helps you that instead of doing this, instead of saying that I will go from here, 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 and then find this element, I will directly hit this element. How? Through direct addressing. Now I explained direct addressing in the first class. I'll explain it again. Let's say I have an array like this, right? And this array is, let's say, of pocket 6. And I have my interest element at array number 5. So that is where I want to go, right? If I want to go at array 5, then how do I go to array 5? You will write the code in C as ARR5, but that is not what the compiler will do. So what the compiler internally does is, I have told you many a times that the name of the array is the starting address of the array. Starting address of the array. So what the compiler will do is, this is the starting address of the array, and this is the next address, 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 and this is the next address, right? So what the compiler will do is, it will say that the name of the array, okay, ARR is the pointer, right? So ARR is pointing where? Name of the array is the starting address of the array. So ARR is actually 1000. So with 1000, if I add 5 blocks, why? Because you have set 5, right? So you have set 5 here. If I add 5 blocks, then what should I get? I should get 5 multiplied by 4 as the skipping bytes in terms of from ARR, whatever that byte was. So let's say ARR was at 1000. So I will say 5 bytes or 5 blocks. Each block is 4 bytes. So I will be skipping 5 multiplied by 4, which is going to be 20. In order to reach what? 120, right? So in order to reach 120, so I will say that I want to go to 120. The way I'll get it 120 is, I'll take the name of the array, then I'll say which index. The index will be translated to the total number of bytes, and that will be added to the offset. Offset will therefore become 1020, and I will say star of this. That means the value at that particular address. So I will say here star of this. So whenever I say ARR of 7 or ARR of 6 for that matter, it also means the same thing, star of ARR plus 6. Internally, it gets evaluated like this. This is something we have already covered in the first class, right? So if you now understand this, can you therefore appreciate the whole point of hashing is what I'm just saying in the next 2 minutes, right? If you concentrate for the next 2 minutes, you will understand hashing. What is hashing, right? So that is what I'm trying to give you. So whole point of hashing is, can we search for this 90 with an order of 1 complexity rather than an order of n complexity? That is what is hashing. Again, I'll repeat. Can we search for 90 with an order of 1 complexity rather than order of n complexity? Right? So that means that I have to directly come here. If I know that I have 90, if I know I have to search for 90, then I have to translate this 90 somehow into this 5. This is my 5. If somehow I know 5, then I can immediately say that instead of searching for 90, I will directly say ARR of 5. That will give me 90. And that will give me a validation whether my 90 is there. So ARR of 5 should contain 90. Whether it contains 90 or not, that's a different thing. ARR of 5 should contain 90. Now, if ARR of 5, if I go directly there and expect 90 there, and I get 90 there, then the search is successful. If I don't get 90 there, search is unsuccessful. So the point is that I am not going to go like this. I am not going to go like this from here, 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 here. I will directly hit 90's index, which is 5. How do I translate? The question therefore is, how do we translate this 90 to this 5? And that's where hashing helps you. So you translate that using something called as a hash function. So using any kind of hash function, and we'll see a lot of hash functions, we will translate the input value that is what we are searching into something that is a index value where we will store that particular key. So instead of having us to go through an array traversal, we will directly hit that array and assume that that array at that index position contains my value, right? So all I need to do is, while storing this, I need to use this hash function. While creating this array, I need to use this hash function, and I need to store my element according to the output of this hash function at that particular index position. So if somebody stores 90 at 5, then he knows the hash function with which he got 5 and not 4 and not 3. So he knows the hash function. I use the same hash function. Then 90 will also give me 5. And therefore I can go to 5, and both of us are actually, he has written it in 5 using the hash function. I am reading it from 5 using the hash function. So everybody is happy and we get everything with an order of 1 complexity. So that's what this particular problem is trying to solve. So that's on hashing. Let me see the chat window if everything is okay. Okay, everything is okay. So that's on hashing, why it is needed, what is it, and how are we going to do it is what we will see. So this is what I was talking to you about, that we have what we are searching for, which we call as the key, and we have the index of the array that will come out of this, right? So this index of the array is what is called as the array list, hash list, or the hash table. So what is there is this particular array where we actually store the key is called as a hash table, where the value of that key is stored. So if I am searching for 90, then that 90 will be stored somewhere here, and these are called buckets. These are called buckets, and this is a simple array. This is starting from 0, 1, 2, 3, 4, simple array, right? Nothing fancy about it. And that array pocket is called as a bucket, right? So each of these index positions is called as a bucket. Each of these index positions is called as a bucket. So if I create an array and each index is a bucket, and somehow I take this data and convert it into an index, then in that index I will store that data, right? In that index I'll store that data. Now how did I convert? So how did I convert? Again, I'll repeat. I have data, I'm converting it to an index where I want to store it. How did I convert? I used a hash function, right? So this, somebody who is writing into the array will use this method. I am reading from the array to find this data. So I will also say data, I will say the hash function, right? So I know what data I'm searching, so I will use the data with the same hash function. So what will it return to me? It will return go to this index, right? I will go to this index, I will directly get the data. That is the beauty of hashing. I hope you have understood. So let us now get to what is the way to hash it. We were talking about hash function, that is the way to convert the data to an index. So the way to convert is one of the most popular method and one of the most redundant method, bakwas method I will say, is division method, right? But it is very popular because it is very easy to understand also. And that hashing with the hash function actually says this is my hash function. So table size says that, what is the table size? I told you, right? What is my table? Hash table is this array. Then the size of this array is the table size, right? So the size of this array will be the table size. So when we say table size, don't get confused. It is the array size where you are keeping the key, right? So where we will be keeping the key. So that is the array. So if my table size is 10, right? Or if my table size is if my table size is 10, and if my key is, let's say, 97, so then I will say 97 modulo 10. So what will I get? I will get 7 as the remainder, which means this 7 is the index in a 10 pocket array. In a 10 pocket array, this 7 will be my index where I will keep what? 97. Right? So that is what this hash function will typically do. So let us take an example here. Same thing, 37 modulo 10 means 7. So what they will do? They will create an array with 10 pockets, and in the pocket number, let's say, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we want to put it in 7th index. So in the 7th index, we will put 37. So that is how this particular example would look like. And to do that, how much time did we take? We went directly there, na? We said ARR of 7 is equal to, or we wanted to say printf ARR 7. This is the read. And when we wrote it, we had scanned into it as what? ARR 7 again. Ampersand of ARR 7. We also scanned it there. Right? So both these operations are order of 1 because they are directly accessing the array memory. And I explained just now how we are doing it, right? Just before the beginning of this class, at the beginning of the class, we discussed that. How it is happening, the direct address is happening. So both of these are the print and the read. Both of them are happening in order of 1. And that's where you are actually getting to see a huge improvement from an order of n search to order of 1 search. Right? But of course, you are compromising on space, you are compromising on when you are putting this, you have to give some more CPU time. All of that is fine, but the ultimate outcome for the end user is very fast. So you have to do some trade-offs to make that happen. And that's what you are doing here. So what is a good hash function? A good hash function is something where you will actually say that the hashing should not produce the same index value for different keys. So you see we have different keys here, but same index is coming. Then what will happen? The array has only one pocket, na? Array has only one pocket. So if all of these are coming to 1, then this is 0 and 1. So 21 will stay here, and next time when 31 comes, then 31 wants to stay here, but 21 is already there. So this phenomena is called as collision. Right? So this phenomena is called as collision. So you are actually going to create hash functions which avoid collision. Right? Which avoid collision, but collision cannot be avoided fully. That's called a pigeonhole theory, and we will explain that also. But then what I'm trying to get at here is that hashing, any hash function that you create, there should be an attempt being made that you will not generate the same index over and over again when your input element changes. Right? So I'm changing 79. If I take 79, then let's say 5 comes out as my index with whatever logic. I'm not saying this logic, some other logic, right? This is a hash function. I can change this hash function, right? So with whatever logic I want, I change it so that I get 5. 69, I also get 5. Let's say 7, I also get 5. then whatever hash function I would have used to actually do it is bad. It's not a good hash function because I'm changing the data, but I'm getting the same index, right? So it's bad because you will actually create collision here. So what is the requirements for a good hash function? There should be a uniform distribution. So if this creates 5, then this should create probably 7. And this should probably create 9. And something else should probably create 1. So you are distributing, not just concentrating here, always. You are distributing. Some of them will come here, one of them will come here, one of them will come here. So you are trying to maximally use the array where you are trying to store your value, right? So that's why uniform distribution. Deterministic means what? Deterministic means if somehow 79 you convert to 5 using a hash function, next time when you do 79 using the same hash function, you should not get 7. Deterministic means if the hash function is the same, if the input is the same, of course you have to get back what? You have to get back 5. You should not get back 7. So it should be deterministic. You should be able to determine that yes, I will be getting back 5. That's why deterministic. Otherwise there is no point, na? Because then writing will be in one index, reading will be from some other index. Fast to compute. All this process should not be an overhead for you, right? So you should be able to finish the H key calculation in order of 1. Minimize the collisions. I've already talked to you about that. So that is on this particular problem. The first method that you saw was the division method of hashing. So we are discussing the hashing methods. So one of them we have discussed already, hashing methods. So one of them is the division method. The second thing that we will discuss now is the mid square method. In the mid square method, what we will do is we will take the key. So 1, 2, 3, 4, I want to convert to an index. Let's say I want to convert to index 27 or whatever it is, right? In this example, it is 27. I just took 27, right? So you can say anything. 1, 2, 3, 4, I want to convert to an index. So what I will do is I will square 1, 2, 3, 4. So we are talking about hash function, let's say H2. So in H2 hash function, which is called as mid square method hash function, we will say that 1, 2, 3, 4, I will put it through some logic. Function is what? Some logic, right? At the end of the day, H2 is some logic. So that logic is that take a square of the number 1, 2, 3, 4 square, you will get this number. And this number takes some digits, let's say 2 digits from the middle of that number. Then we will see that we are getting 27 from the middle of the number. And because we have a 100 pocket array, these 2 digits will always be less than 99. Right? From 00 to 99 is what these 2 digits will be. Any combination of that. And then I can easily fit that combination into my array index because I have a 100 pocket array. Right? So what I get from those 2 digits, I get here 27. Now why are we doing this? The reason why we are doing it is that first remember one thing. What is your basic principle? Shouldn't you think that this 27 needs to have some properties of these 1, 2, 3, 4 because it is generated from 1, 2, 3, 4, na? So 27 needs to have some properties of 1, 2, 3, 4. Otherwise, how will you correlate? I mean, then somebody else will also come, let's say 7, 6, 9, 9 and also generate 27. If this to this does not have any correlation, then this to this will also not have any correlation. Then you definitely don't know how this number gets generated or this number gets generated. So what I'm trying to say is, if 1, 2, 3, 4 influences 27, then 7, 6, 9, 9 cannot influence 27 because it's a different number. So that means that 27 should have some amount of, what do I say? So 1, 2, 3, 4 should have some amount of control on generating 27. Now typically if you see squaring, then the first digits actually influence the first part of the numbers. The first digits influence the first part of the numbers. The last digits influence the last part of the numbers. Whereas the middle digits are actually getting influenced by the overall number. And that is why we take the middle digits. This is the answer to that. Again, I'll repeat. When I take any number and try to square it, the first digits influence only, or I would not say only, the first digits influence the first part of the numbers. the last digits will influence the last part of the numbers, right? And the middle digits will influence the overall number, right? So that is why I'm saying that we will take the middle digits, because there the characteristics of this number will be there. That means that if I take the middle digits from here, this middle digits will actually have some characteristics of this entire number, not just 1 or 2 digits. And that is the mathematical significance of why we will take the middle digits. Now, how many digits? That depends on your this one, hash table length, right? So hash table length means what? Length of the array, right? So if your length of the array is 100 pockets, take 2 numbers. If your length of the array is 1000 pockets, take 3 numbers. If your length of the array is 10 pockets, take 1 number. So that is how mid-square method works. Folding method, again a similar method, where we will take the digits and we will simply say that we will divide it into parts. Now these parts will be different depending on the hash function, but let's assume that the parts are 3, or the parts could be 4, or the parts could be a variable part. Then whatever the parts you are taking, these parts, if you start combining these parts together, you will get some number. And that same number, do a modulo with whatever size of the pocket you have. So that is the length of the hash table. Length of the hash table that you have. Length of the hash table means length of the array. Right? So if I have the length of the array as 1000, then I will modulo it with 1000. Because any number, if I modulo with 1000, will always be less than 1000. So it will fit in my array. So what I'm saying is 1035 has come, modulo it, you'll get 35. So in this 1000 pocket array, I will put it in the 35th index position. Right? So that is what we talk about in the folding method. Collision, I have explained to you that both the a key K1, once it is hashed with let's say hash function 1, produces an index let's say I1. A key K2, if it is hashed with the same index with the same hash function H1, will produce the same index I1. Then we have a problem, because these two keys were different, but you'd ask them both to go to one destination, I1, and that is a collision. Collision is unavoidable. This is very, 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 very important pigeonhole principle, which says that your size of the array where you are storing these are always going to be less than whatever data is your incoming. So are we saying that if I have 0, 1, 2, 3, 4, 5, 6, 7 pocket array, then this can support or will support only let's say 7 input data elements? Then I need not need a hashing function at all. If my input also has 7, my output also has 7, I will obviously say, okay, 0 number data, please go to 0, 1 number data, please go to 1, and so on and so forth. 7 number data, go to 7. That's all. But I have larger number of data now on the left hand side. Here I have more data than what I have here. That is why collision will happen. Right? So the 0th index or 0th data that came in might need to go to, let's say, 0. The first data that came in, 1 index data, in fact, let's not call 0 index data. Let us say that the first data that comes in goes to the 0th index. The second data that comes in might go to the, let's say, 6th index. The third data that comes in might go to 5th index. And in this way, when I say, let's say, 10th data that comes in, it might go to, let's say, 2nd index. And 11th data that comes in, it might go to, let's say, I say 6. So what is happening here? Here what is happening is that this 6 and this 6 are the same. Right? So my data is different, but the outcome is coming to be the same. Why is it happening? Because my total number of data is of course going to be greater than 6. My total number of data can range to 100. So for a 6 pocket array, I have 100 data that is incoming. Then why will I not take 100 pocket array? Because it is costly. And then why will I take why will I take 6 pocket array? Why not 50 pocket array? Why not 70 pocket array? Why not 30 pocket array? That's because your data that is there will influence based on common experience, that if I have 100, then it is okay to have 10 pocket array, because all the data will not be frequent. So what I'm saying is, let's say the word, let's say good is a data. The word good is a data. So good comes in, let's say out of 100 times data comes, out of 100 times data comes in, good comes in 30 times. The word bad is a data. This also comes in 30 times out of 100 times. The word fair is a data. This comes in, let's say, 20 times. And then there is some more data, right? There can be so many other words. There can be hungry, there can be full, there can be good, boy, there can be girl, right? So many data points are there. So I can actually easily take this beyond or rather to 100, right? So all these 100 words that will, or not 100 words, I would say less than 100 words, right? So if I say that good is one word, bad is one word, fair is one word, hungry is one word, full is one word, then boy is one word. In this way, can I go to 100 words? I can go to 100 words, right? And that is how the data will be. It will be 100 words. So for these 100 words, good comes 30% of the time, bad comes 30% of the time, fair comes 20% of the time, hungry comes 1% of the time, this comes 1% of the time, and so on and so forth. So if I go down, it's going to be 0.5% of the time, something like that, right? So then what am I trying to say? That though you have 100 data points, all the data do not come often. That means it is okay to have what? I definitely need a placeholder for good, I definitely need a placeholder for bad, I definitely need a placeholder for fair. So with 3 pocket only, I should have been good, but I'm increasing this to, let's say, 5 pocket. So that means most of the time, 90% of the time, 90% or 80% of the time, 80% of my time, this array will be good. This array is okay, because good will find one spot here always, bad will find one spot here always, fair will find one spot here always. 80% of the time. Why? Because good comes 30% of the time, bad comes 30% of the time, and this comes 20% of the time. So that creates 80%. So they will have one spot reserved always. Only thing is when this hungry comes, then boy comes, then something else comes, then we have an overflow here. Because they will go to the right side of the array, and then only 2 pockets are left in the right side. So, but I have so many elements, I have probably 80 more elements here. And if they don't come often, whenever they come, if both of them come together, then my array is full, and the third time somebody else comes, there is a collision. So the collision is not going to happen often. So collision cannot be avoided. Collision has to be limited. So that's how I'm saying that I'm going to structure this. So I hope I've been able to explain to you collision and why it happens. Now, if I actually take collision and try to see what are the resolutions, then one of the resolution of collision is that this is called as separate chaining method. So this is the first method of collision handling. So remember, we have done 3 methods of hashing. First method was division, second method was mid square, and the third method was folding, right? So the third method here is folding, where we took the where we divided the number into 3-4 blocks and we added those numbers, and then we did a modulo. So remember, there are 3 methods to hashing, and then there are 2 or 3 methods to collision also, collision detection also. One of the methods is separate chaining. What is separate chaining? Separate chaining says that you will, instead of storing the actual value, let's say 95 was my key and with 95 I found that the index is 7. So when I go to index 7, I don't store 95 there directly. I will create a pointer to a linked list, and there I will store 95. Right? So if you know that 15 creates, let's say, 7 as the index, if you know 25 creates 7 as the index, if you know 35 creates 7 as the index, what am I writing here? I am writing all collisions, because the data has changed but the index is the same, and my hash function is h1, h1, h1. The hash function is the same. So as I said, collision cannot be avoided. So this will definitely happen. When it happens, how do you avoid? How do you rectify it, or how do you minimize it? So that is where I'm saying that, okay, 15 we were supposed to put where? We were supposed to put 15 here. So in, let's say, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 8 and 9. So I have a 10 pocket array, ARR 10. And in this ARR 10, I am trying to put what? I am trying to put 15. Where? In the 7th index. So I will put 15 here, but I am not going to put 15 here. If I put 15 here, what will happen is, when 25 comes, it will create a collision. When 3 comes, it will create a collision. So instead of putting 15 there, what I will do is, I will create a linked list. I will create a pointer there. So this will be a pointer, and my linked list will be here. And I will say that this 15, I'll put in the linked list first element. And this is, let's say, at 1000. So I will store 1000 here. So now this starts pointing here as if it is the head of the linked list. Right? So 15 will be there. And then if 25 comes, 15 is okay. 25 comes, 25 will come here. 35 comes, 35 will come here. So what you get when you try to read is that when you say 25, I want to see if 25 is there. So 25 will generate for you what kind of hash? 7. So 7 is the index. So you'll go to 7, and in 7 you'll find a pointer. So go to the pointer and traverse the linked list. You'll get your 25. This is much less costly than actually getting to search it in a huge amount of space. So instead of an order 1 complexity that we were trying to achieve, we will now get into order n complexity if all of these keys fall into 7. If the entire data set of 100 fall into 7, then all the keys will be here. All the keys will be here. That's why the worst case is still order of n, but it will not be that much, because you will be intelligently designing it so that all these pockets are used. All these pockets are used to store one head pointer. So this will store one head pointer where you will again start one more, let's say, linked list. Right? So any hash function that returns 0 will come here and will start storing number 29, 35, or whatever it is. Right? So that is how the collision separate chaining method works. Open addressing method, there is 2-3 ways of open addressing method. One is the probing rule. Probing rule says that whatever hash you got, suppose I have to put my, this is my hash table, right? So this is my hash table which is empty. I have got 58. This 58 I am utilizing the division function. The division function to create the hash. So the hash says that you have to go to index number 8. So I go to index number 8. So somewhere here will I store 58. Then 18 comes. 18, I also use the same hash function. I get 8. So then I will get a collision. So what I will do is, then I'll say, okay, 8, add it to 1. So this is the probing. Probing means that 8 added to 1, you will get 9. So now 9th slot is empty, then insert that there. Which is what we will do here. We will say that, what was the value? 18. So 18 will be inserted here. Next 89 comes, we get 9. So now 89 has a clash with 18. Right? So then again we will add 1 to it and we will get 0. So 89 goes to here. I hope you are understanding what is happening. Now if you have multiple, if this was also, if adding 1 also created a collision, then you will start adding 2. If that creates a collision, you will start adding 3. That is what this says. I, first you will add I, then you will add I plus 1, I plus 2 and so on. So that is what is probing. So that way you are avoiding, when you detect a collision, you are utilizing a probing method. Probing method means you are trying to see, probing, trying to see if doing something else changes the index and you can actually reach a proper destination. Quadratic probing is the same thing. Only thing is, instead of I plus 1, you will do I plus 1 square, 2 square, 3 square and so on and so forth. Why it is better? Because it eases off the gap. So instead of just adding 1, 1, 1, 1, 1, 1. So suppose you are here, you already have an element here, and your new person that is coming, new key that is coming, also wants to come here, right? So then what you will do is, you will add 1 and 65 comes here. Instead of adding 1, if you would have added I plus 2 whole square, then you would have shifted this from 1 to here probably, 65. That means you would have moved away from this place. The more you scatter, the better, because then you are utilizing the array much better in terms of finding white spaces, which is why quadratic probing is much better than linear probing. And the last method is double hashing, which basically talks about that if I have a key like this, let's say I have a key like this. Let me take an example. I will explain with an example. So we have m equal to 10. What does m equal to 10 mean? It means that my hash table has 10 pockets. That is what m equal to 10 means, right? So that is the length of my hash table. And I have got what? I have got, let's say, 58. So 58 with mod 10 funda, with a h1 hash function, which is k mod 10, will give me 8. Right? So if I take 8, which is 58, so I will store 58 here. Now if I store 58 here, the next element that comes in is 18. 18 also gives me with what 10, 8. So then what I will do is, I'll calculate a second hash function. And this second hash function, the formula of that is r minus key mod r. That means, what is r? It is the first prime number before 10. First prime number before 10 is 7. So that is r. So 7 minus the key. What is the key coming in? 18. Mod 7. Again the prime number. So that gives me 3. And this 3 becomes my step size. What is my step size? The step size will be used to, instead of saying that, see, you remember what we were doing earlier. We were saying that whatever the number came, whatever the index value came, that I that was coming, we were increasing it by 1, or increasing it by 1 square, or increasing it by 2, or 2 square. We were doing that. Instead of that, this is called a step, right? So instead of that, what we will say is, this will come through this function. The step will come through this function. So instead of 2 square, 3 square, I will get that number from here, 3. I will get that number through this calculation itself, rather than relying on a hard-coded number. So I'll get the number through the calculation, and then I will use the 8 that was creating that collision, which is this, right? So the 8 that was creating the collision, that index, see, the index only I was adding to that 2 square, 1 square, 3 square. So here also the index I am adding to 1 multiplied by 3, or 1 multiplied by 4. Depending on what your number is, whether it is 38 or 18, your step will be calculated basis this second function. So this step will start influencing your index addition rather than hard coding. So I will not say I will get increased with 1, or I will get increased with 2, or I will get increased with 1 square, or I will get increased with 2 square. I will say I will get increased with a step, and that step is equal to your h2 function, which is r minus key mod r. So get that from here, put the step here. That is much more scientific than saying hard-coded increment. And with increment, what are we trying to do? We are trying to avoid that index position and go somewhere else. That's all we are trying to do. The last thing about hashing is the load factor. Load factor is this, that if my hashing is, let's say this is my 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if my total number here is 10, total number of elements is 10, then my hash table size is 10. So this is what this table size means. Hash table size. This hash table size is 10. So this hash table size that is 10 now says how many keys are here. Let's say my key is here, 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 key is here. How many keys are there? 8 keys are there. So 8 divided by 10 is 0.8. What does that mean? That means your hash table is getting full, right? So less than 0.7 means the table is sparse. That is, it is not full. You can have, the collisions will be minimum. But when it is greater than 0.9, the collisions will be very frequent, because obviously every element is full means there are chances that that element will come again. Right? So that is why then we have to rehash. Rehash means that we will have to increase this particular space. That is what is rehashing. So you'll have to double. Normally we do a double array. So if we started with 10 and the 10 and the table got filled up after some time, let's say 1 day, 2 days, 10 days, 1 month, right? The table got filled up. Then we will rehash it. We will say 10 array now becomes 10 array will now become 20, 20 will become 40, 40 will become 80. That is what we will say. I have explained the advantages, disadvantages. So that is all that I had. Now let's cover some questions. Most of it I have covered. As I said, my entire lecture series is based on university questions only. So I'm not covering university questions separately. So still, if you want to see what comes, what is hashing, describe any 3 methods. We have talked about division, mid square, folding. Then comes discuss different collision resolution techniques. Collision resolution techniques, we have talked about 2 of them, separate chaining and open addressing. Open addressing has these kinds. Open addressing was that thing, if you remember, I plus step. Right? So step can be I plus 1, I plus 2, I plus 1 square, I plus 2 square, or I plus step that comes from a secondary hash function with that prime number concept. So that is what is open addressing. And then we have some MCQs also coming. Which of the following is a hash function? Of course, folding is the answer. None of these are hash functions. Probing and chaining are not hash functions. They are collision detection functions. So be careful on that. Which of the following is not a requirement for a good hash function? So what are we trying to say? In a good hash function, are we trying to reduce storage space? No. As I said, we have to rehash, you have to increase storage. We are not trying to reduce storage space here. Storage will be compromised. Why? Because you are trying to gain speed. Right? So these 3 are a typical triangle. Speed, cost, memory. You try to change one, the others will change. You try to bring down your speed. The triangle size has to remain constant. Therefore, memory might go like this. So memory increases or decreases if you try to bring down speed. Cost increases or decreases. So they are in the 3 quadrants of a triangle, and that's why it's very difficult to create a balanced triangle by adjusting all the 3. Somewhere some trade-off will have to be made, and this is the trade-off we are doing for hashing. Space we are not worried about in hashing. Our main goal is speed. Ratio of items present in the hash table versus total size is load factor. Just now we have discussed that. Define hashing. What are the different types of hashing? What are the advantages of hashing? We have all done that. All of that is covered. So I hope this has been clear now in terms of what is hashing. We finished hashing. We'll get into graphs after this. Let us do a quiz. Let me see the quiz box. Okay. Ketchup Night. Sir, will you be doing DA with us too next semester? Ketchup Night, I don't know which college you are. If you can tell me the college, I can confirm you. But next semester DA, I don't think has been yet assigned to me. because it's still not assigned actually. So we have not discussed with the HODs about it. But anyway, I teach or not teach, DA, if you want my help, you will get my help. Is the audio muffled? We discussed that. The array size is the limitation of hashing. Yes, array size is the limitation, definitely. That's where the collisions come in. But then you have to rehash. As I said, space is not an issue. You will increase the space. For a single target, then division method is fine, but falls on the multiple target searching as modular problem. To search for a single target, then division method is fine, but fails for multiple target searching. Yeah, I mean, that's the problem of collision, right? Multiple targets will only create collision. So that is why our searching cannot be just for dum-dum. We will be searching so many things. We will be searching Godia. We will be searching Metro. We will be searching this thing, that thing. So all of that should point me to a different direction or different index of the array, right? And that index should be available. So that's where the collision will start if you have not carefully thought about it. Mid square, the square of 23 is 529. How come we get 523? Similarly, how did we get 756? Square of 23 is 529. Okay, let me see what that was. I didn't square 23. Who said I squared 23? I squared 1, 2, 3, 4. 1, 2, 3, 4 square is 1522756. From there I took 2 digits from the middle, which is 27. So look here. I will highlight things. First, our target is 1, 2, 3, 4. So we will square 1, 2, 3, 4. Square 1, 2, 3, 4 will give this big number. From this big number, I will pick up the middle 2 digits. And that is 27. I hope that clears what confusion you might have. In load factor, in load factor, if for greater than 0.9 we increase the size, then how the pigeonhole principle works? Will keys greater than table increase? Not really. See, you might have 100 keys, which is a good question that you asked. See, you might have 100 keys. And these 100 keys are here. 1, 2, 3, 4, 5, 6. They have some frequency. We talked about that, right? 20% times, 10% times, 3% times, and so on and so forth. These frequencies are there. Now, what is this frequencies based on? This is based on some historical data. That historically it is seen that they come so many times. According to that, you said, okay, let me create a 10 pocket array. I am good with a 10 pocket array with this history, with this historical data. Now, this historical data slowly changes over time. And this particular person and this particular person who were 3% now slowly become 10%, 10%. They start coming more often. Then what happens? Collision increases. So the keys get full. Right, the hash table gets full. So then you start increasing this hash table. So you will have to increase this. You will have to go beyond this and increase this, right, beyond this. So is your data changing? No, the data frequency has changed, but it could have changed also. Your 100 keys could have become 1000 keys. But definitely if your 100 keys become 1000 keys, it's not called rehashing. You have to rehash. Even before your hash table gets full, you know it will get full because your data has increased from 100 keys to 1000 keys. You know your hash table will get full. That is not a creation logic for rehashing. It is implied you have to rehash. But I am talking about if your data is the same, number of keys are the same, then should I rehash or why should I rehash? Because these frequencies have changed. They are now coming with a different set of frequencies. And you have to accommodate. Right? We have to be agile and accommodate to that. So we will double it. Then we will double this. Then we will double this. Right? So this way we will increase. So I hope this is becoming clearer. How valid is to apply hash tables in linked list? Address is at linked list becomes an easy access. I didn't understand, Farhan. Are you talking about that instead of storing the data, we will store the address? If that is the case, I can answer the question. Just answer what you want to mean. Suppose I have an array like this. Farhan, please answer my question. Are you saying that instead of storing the actual key, 79 is my key, so I will not store 79 here. Instead, I will create a pointer to a linked list which stores 79, and likewise it might store some other keys also if there is a collision. Is this what you are asking about? Okay, Farhan, I don't have your answer, so I can't answer. But let me answer generically then. So 79 is a data. 79 through some hash function, h of 79 gives me 3. So I will store 79 here. But if I store 79 here, another person which generates 3 will be collided. So instead of storing 79 in 3, I will store 79 in this linked list. And this linked list will have a starting address. This address I will put in the 3. So with that, I know that when 79 comes, I know that this will be 1000. That address is where I will go. I am sure that any of these elements I will get 79. So there will be some amount of iteration here. It is not exactly going to be order of 1. Yeah. So it is no different because there is no sequential access. Now I understand, Farhan, what you mean. There is no sequential access of that array. That array is always accessed with an order of 1. Now, as long as you know your linked list where they are created, you are free to do it. So if you are saying that instead of array, I have my data or I want my hash table to be as linked list, right? So I want my hash table to be as linked list. The problem here is that this linked list will be created at 1000. This is probably created at 900. This is probably created at 650. This is probably created at 2000. So instead of an array, if you rely on this linked list for storing your, for creating your hash table, then given a key 79, how will you generate something that is so random? You could get 900, you could get 650, you could get 2. How do you know that what address that linked list will get created? So you need to reach to that address of the linked list directly, because it's an order of 1 is what you are attempting, right? So how will you go there? How will you put your element there? That is the question. You can't. So there is nothing best, Anish. It depends on what your input data is trying to say. If input data is stock data, use something. If input data is people data, use something. It depends on how the data are refreshed, how the data is categorized as different categories like genres, like clusters, right? So it depends on the data. There is nothing good or bad, but I can say for this much that this particular thing, which is division, is crap. This will definitely generate collision. Okay, so should we get into, Acha, Farhan has responded something. If we generate an address using a key, that new address will become, how do you know that address is free? You don't know the address is free, now you don't have control over that address. You cannot create a node at an address. You cannot force the creation of a node at an address. So don't rely on an address that the key will always generate that address, and that address I will go, I'll get something. That's not how it works. I hope you understand now, Farhan. Okay, so now let's get into quiz. Where is quiz? Where is quiz? Where is quiz? Here is quiz. Okay, chalo, hashing. Not hashing, sorry. Why this is called hashing? Okay. Come on, quickly. We'll start at 80. Yeah, we have 80. We'll start off. $73, good start. Order of 1 is the answer. Mihir Surapu, I'm seeing you for the first time. Rest I have seen. Good. You are contributing, nice. To avoid collisions completely, no. To sort data efficiently, no. To reduce memory, no. So to avoid collisions completely, you cannot, right? Pigeonhole principle says that you cannot. So that's the answer. Next. $75, okay, good. Anushka, in fact, I'm seeing you here also for the first time, I guess, but that is good. Where is Shayon? I don't see Shayon. काला जादू नहीं काम कर रहा है. Anish, Kitika, Shayan. Now Shayan comes. What were you doing, Shayan? Anish Nandi, good. I'm seeing you for the first time. 81% accurate. Key mod M. This is what the division method is. Yes. Good. You're listening. Wow, 86. Looks like all of you have listened to this nicely. 2 different keys mapped to the same index. Very good. Very good. $89. Good. Answer is 1. Farhan has come as number 3. Good. Ending this, let's see what is the result. Okay, Farhan, Shayon, Gitika. Good. Gitika, at least you are displacing people who are well known to come first, second. Thank you. And keep contributing. Okay, 79% is the class accuracy. See, this is the best class accuracy that we have had. So probably this hashing thing you have understood much better than the rest of the topics. Good. Keep the interest levels at this level, and I'm sure graphs will also be easy for you to understand. It's not any rocket science. The graphs is a very easy thing for all of you to probably capture. Most of it is theoretical, but we'll see. So I'm switching windows and we will start graphs now. Okay, so this is your graph. A graph is actually a generalized tree. That is something that you need to always remember. It's a generalization of trees, right? So unlike trees, graphs can have cycles. So cycles means, have you seen a tree like this, where this particular tree is linked to this particular, or this particular node is linked to this particular node? That is not possible in a tree, but it is possible in a graph. Right? So we can have a cycle graph, and a graph can also be disconnected. Disconnected means that you have something like this and you also have something like this. Both put together is a graph. That is possible. But this tree is not possible because these trees are disjoint trees. So you cannot say they are one single tree. But as a graph, it is one single entity. Disjoint graphs, disconnected graphs. So cycles and disconnection are two important differences between graph and trees. What do we call these? Let's say in a graph, yeah. So let's say in a graph, if we have these circles, what do we call them? We call them as vertices, written as V. These are called edges, which you also know from your tree days, written as E. And the total number of vertices is the order of the graph, which is the total number of vertices. Right? So the order of the graph is written, the total is actually written like this. The total number of, the size of the graph is written as the size of, or the total number of edges, written like this. So these nomenclatures are important. A graph is written like this. This is how you present a graph. A graph is a function of this particular vertices and these edges. So both of them put together create a graph. So that's why a graph is a function of vertices and edges. That is how you will write a graph. So you have understood what is a vertex. Vertex was actually node in your trees. Edge was edge. Order of a graph is total number of vertices. Size of a graph is total number of edges. That's what we are taking away from here. So in this case, our vertex are here. You have to represent all the vertex inside a set. So you'll have to use this nomenclature to put all the vertices A, B, C, D, E, F, G inside a set. And the count is 7. Therefore, my order of the graph is 7. In terms of other terminologies, if you see here, vertex is 6. Yes, we can count that. 1, 2, 3, 4, 5, 6. These are 6. And the edges is 1, 2, 3, 4, 5, 6, 7. So the edges are 7. What is adjacency? Adjacency is adjacent, right? So it is related to something being adjacent. A and B are adjacent if there is an edge between A and B. So the edge is typically written as E, A, comma, B. That means there is an edge which is between A and B. That is how you write the edge. The edge between A and B, if it exists, then A and B are called adjacent. Right? So can we say in this diagram that D and E are adjacent? We cannot, because there is no edge here. There is no edge here. So these are not adjacent. They are not joined by an edge. Next, incidence. Incidence is edge B and E is incident on both B and D. Edge B and E is incident on both B and D. That means we were talking earlier, adjacency talks about what? It starts from a vertex. So adjacency, we will have to think about the vertex is connected through edge or not. Whereas for incidence, we will think about the edge is connecting to which vertex. Right? So edge is connecting to which vertex. That means AB edge or BE edge in this example is connected to B and E. Therefore, we can say that B and E edge is incident on B and E vertices. So this is the difference between adjacency and incidence. Adjacency says, is my vertex connected with an edge? Then those two vertices, these two vertices will be adjacent to each other. And this edge will be incident to B and D if there is an edge between B and D. That is incidence. Now, so if you see this isolated vertex, what is isolated vertex? These are terms and terminology, 1 marks, sometimes here and there it will come. Isolated vertex is what? Isolated vertex is a vertex with degree 0. Right? So isolated vertex means something like this. What is a degree? Degree is the total number of edges. Right? Degree is the total number of connections that you have to that particular. In fact, we'll have the degree definition after this. Let me see if the definition is there. Then I will skip this for the time being. Where is my degree definition? Yeah. Degree is the number of edges touching a vertex. The total number of edges is what I was trying to say. So here you do not have any edge. This is all. This is all. This is a graph. Yes, this is a graph. There is no edge, which is okay. So then this is called an isolated vertex. Pendant vertex is like this. Suppose you have like this, then pendant vertex is vertex with degree 1. So if you see this vertex, it has degree 2. Why? Because there are 2 edges connected to it. If you see this vertex, there is degree 1. Why? Because there is only 1 edge. This vertex, only 1 edge. Right? So this is also degree 1. Any degree 1 vertex means it is a leaf node. Or leaf, I wouldn't say node, it's more of a leaf vertex. And that is basically called as a pendant vertex, right? What is a pendant? You have seen your mother, sisters wearing like this. This is your pendant, right? So the pendant is on your that locket that we call, which is on a chain. So this is the leaf pendant. After this, nothing is there, right? So there are no children after this, which is why the degree is 1, and hence it is called a pendant. Universal vertex is which is connected to all the vertices of the graph. So if I have a graph like this, and if I say that then this is a universal vertex, this is a universal vertex, this is a universal vertex. Why? Because this vertex is connected to all the vertices, all the other vertices, connected to this as well as to this. Likewise, this vertex is connected to all other vertices with this and with this, and likewise this vertex is connected to all other vertex which is this and this through these two edges. So that's why all three of them are universal vertex. Simple graph looks like this. Now simple graph looks like this, and it is saying that what is the max number of edges. So max number of edges is going to be v into v minus 1 by 2 and we will come to this derivation shortly. Hold on to that derivation. How v into v minus 1 by 2 is coming, there is a important theorem that we will understand for that. But this is a simple graph. There are no loops, there are no parallel edges. So you cannot have a parallel edge like this and you cannot have a loop like this. Then it doesn't become a simple graph, right? So this is not a simple graph. Multigraph is like this with a parallel edge. Pseudograph is with a loop, and weighted graphs are where you have your edge saying that what is the cost. Cost means let's say from A to B, let's say this is a distance. So this is, let's say, Newtown, and this is, let's say, Dum Dum. Then what is the cost to travel from Newtown to Dum Dum? That is what I mean by cost. Cost need not be always monetarily. Cost could be CPU time, cost could be resource, cost could be anything that is quantitative to actually go from A to B. So that's on cost. Degree we just now talked about. The number of edges touching a vertex is a degree, right? So that's what is a degree. And if there is a loop, then we will count it as 2, because there is an outgoing degree, outgoing edge like this, and there is an incoming edge like this. So yeah, so there is an outgoing edge and then there is an incoming edge. So this is my one outgoing edge and this is the incoming edge. So this will be 2 degrees, because how many edges are connected to this circle? These are 2 edges connected to this circle. So which is why we will count it as 2 for the loop kind of a graph. Now if I calculate here what is for C, how many is the degree? Total number of edges is the degree. So we have that is connected to it. So it has connection here, here, here and here. So that is why the degree here is 4. Whereas degree of A is how many connections? Degree of A is 1, degree of B is 1, degree of D is 1 and degree of E is 1. I hope you understand now degree from this. Now the theorem that I was talking to you about is the handshake theorem, and questions come from handshake theorem against this topic. So this topic says that the degree of a particular vertex, if I sum the degree of the vertex, then I'll get 2 multiplied by the number of edges. This syntax I told you is the total number of edges, right? So total number of edges multiplied by 2 is the total number of degrees of each and every vertex of the graph. So if I take a graph like this, if I take a graph like this, then the total number of degrees, the degree of this particular node is going to be 2. The degree of this particular node will also be 2, or vertex will be 2, and degree of this will also be 2, right? So all these 3 degrees will be 2. Then summation of all the 3 degrees will be what? 2 plus 2 plus 2, which is equal to 6. And can 6 be made equal to 2 number of edges? What are the number of edges? 1, 2, 3 edges, right? So 6 definitely is equal to 2 into 3 edges. That is why it is satisfying this equation. So number of degrees of a vertex is equal to twice the number of edges. So that's on that topic. Now coming to this came in your universities, I think last year or last to last year. There are 21 edges. There are 21 edges. So we create this formula. There are 21 edges and 3 vertices have degree 4, others have degree 2. Find the total number of vertices. So it says total number of vertices, how many it will be. So I have only one formula to go with. This is the handshaking formula. With this formula only, I'll have to do all typical these kind of sums. Now, if my edges are 21, then my sum of the degrees will be 2 multiplied by 21. Why? Because my handshaking theorem says 2 multiplied by the total number of edges is the total number of degrees. Total degrees of all the vertices. Total degrees of all the vertices. So 2 multiplied by 21. 2 multiplied by 21. Why? Because 21 is given as total number of edges. Will be equal to my total number of degrees. So that is the first part of the solution. So this is what it is trying to say. That 42 will be equal to the total number of degrees. Now degrees, this will be broken up into two things. Something will come here and something will come here. So this will be a summation of these two things. Right? So what will happen here? Let us see. Degree of 3 vertices. Degree with 3 vertices is given as how many? See, 3 vertices have degree 4. So if 3 vertices, they are already mentioning 3 vertices have degree 4. So how many total degrees we have? The first vertex has degree 4. The second vertex has degree 4. Third vertex has degree 4. So 3 vertex has degree 4. This is what this means. 3 vertices have degree 4. What is this? It is 3 multiplied by 4, which is equal to 12. So this 12 is what is already known to me. So I am saying total degree, that I found that 3 vertices have degree 4. Right? So if I multiply this, I will get one portion of the total degree. Why? Because need not be that there is only 3 vertices. There are more than 3 vertices, and that's why they are saying find the total vertices. So now if I can substitute something here, then I can get the total vertices. So that's where I'm saying that this, if I take it as x, that is the remaining degree, then x is equal to 42 minus 12, which is equal to 30. Right? So x is equal to 42 minus 12, which is 30. Now there are remaining vertices have degree 2. Then how would they be created? They will be created like this, na? 2 multiplied by that particular vertex, whatever that vertex is. So it will be 2 degree, right? So all the vertices will have 2 degree. So all the vertices will be like this, the remaining vertices. If I add their degrees, they are degree 2, na? So they will be like this. So what is 30? 30 is 2 into the number of vertex which is having degree 2. Right? So 30 will be 2 into n. So this is the remaining, right? What was the remaining? Remaining is saying all other have degree 2. So this is degree 2 and these are all other. All other multiplied by degree 2 will be the total degree that is left off, and which is what is 15. Right? So what is these are the other vertices. But you already had 3 vertices. Right? This portion of the equation, you already had 3 vertices. So 15 plus 3, the total number of vertices is what they have asked. 18 is the answer. I hope you understood. Easy, plus minus. So that's on this particular problem. In degree, out degree, if you have a directed graph, now we are talking digraph. Digraph means directed graph. Directed graph means it is having an arrow like this. You can only move in this direction. You cannot move the other way around. So this is a directed graph. It has an arrow. So then the degree here will be 2 different degrees. One will be in degree, which is if the arrow is coming inside of you, then this is called as in degree. So this is 1 in degree. Right? So and then this is 2 in degree. And if the arrow goes out of you, then this is 2 out degree. So this is in degree and out degree. and the summation of your in degree and out degree is the summation of the total number of edges. Quite natural, right? Because if a graph is like this here, this in degree is how much? This in degree is this is the arrow in this direction. So the in degree here is 1. Here the out degree is 1. Here we have the in degree as where are we? So here the in degree is out degree is 1, in degree is also 1. Out degree here is 1, in degree is 1, out degree is 1, in degree is 1, out degree is 1, in degree is 1, out degree 1, in degree 1. So you see, if I just sum up the in degrees, I will still get the total number of edges. So my sum of in degree is equal to my sum of out degree is equal to my total number of edges. Right? So that way, this is how the total number of edges would come. So that's on this. Connected graph I've already mentioned. Okay, connected graph. One thing you have to remember of a connected graph: path exists between any pair of vertices. That means if I take a graph like this, then path exists between every pair of vertices. This is not a connected graph. Now it has become a connected graph. Right? So where one path exists between every pair of vertices. That is, from this vertex I can go to all other vertices. Similarly, from this vertex I can go to all other vertices. Then the minimum edges, how much it will be? The edge is, this is 1, 2, 3, 4, 5, 6. 6 edges are there. 6 edges are there. And how many vertices we had? We had 1, 2, 3, 4. So vertices we are having is 4. Right? So minimum edges for a connected graph with n vertices is n minus 1. We have not talked about minimum here. Right? So we are now need to talk about the minimum vertices. So when we talk about the minimum vertices, just imagine a situation where, let's say, from a particular vertex, I have to go through these vertices. Right? So if I have to go through these vertices, can I just keep the graph like this and this? I can't, because then this is not a connected graph. So if this graph has to be connected, then you have to actually put the minimum. In fact, if there exists a pair between every pair of vertices, means that the way you want to treat it is that this particular index or this particular node is connected to this particular node. This particular node is also connected to this particular node. How many edges have you created? You have created 2 edges. And how many indexes you had? You had 3 indexes. Right? So, or rather, how many, what do we call, vertices you had? You have 3 vertices. So for 3 vertices, you need to have minimum 2 in order to make sure that at least these edges or each of the vertex is touched once by at least one edge, and that's when you will get a connected graph. Now that's from a connected graph perspective, we will need to calculate a formula which says that this particular thing, where is that formula we saw in the beginning? I said we'll do it later. This one. So from a connected graph perspective, we will have to calculate this formula, v into v minus 1 by 2. So we will be doing that. Let me go ahead. I will show you where we will do that. This is okay. Now adjacency matrix is the next topic. In the adjacency matrix, the problem is a graph is a pictorial description. How do you put it on paper? That is, or rather, how do you put it inside a data structure? So to put a graph inside a data structure, you typically use a matrix form. Right? So you'll use a matrix form to put a graph inside a data structure. And that matrix form is what you see on the screen. What are these? These are saying vertex, vertex. So I'll put all the vertices here. Now if I draw this, let me draw this graph. Okay, we will say 1 is connected to 2, 2 is connected to 3, 3 is connected to 4. Not 3 is connected to 4, 2 is connected to 4. So this is a graph, right? This is a very very simple graph for that matter. How do you represent this graph in a data structure? Let's take a matrix. So we have put 1, 2, 3, 4 in the rows, 1, 2, 3, 4 in the columns. Why 1, 2, 3, 4? We have these many vertices. That's why we have put 1, 2, 3, 4. So these 1, 2, 3, 4 that we have put, what is the connection between 1 and 2? 1 is connected to 2. So 1 is connected to 2. That is why you have 1 here. Right? 2 is connected to 3. So 2 is connected to 3. You have 1 here. And 2 is connected to 4. So 2 is connected to 4. That means you have a 1 here also. So if I give this matrix to you, immediately you can draw this graph. And that is the whole point. Can we store it in such a manner that we can start drawing it also from that matrix? So that's on the adjacency matrix. There is something called adjacency list also, where you have a name value pair. That 1 is the name and the value of that 1 is this. So this is the name value pair. In this name value pair, what are you seeing? You are seeing that 1 is connected to 2. Is 1 connected to 2? Yes. 2 is connected to 3, 4. 2 is connected to 3. 2 is connected to 4. So you can write it like this also. 3 connected to null, 4 connected to null. Perfectly fine. So this is called adjacency list. Right? So, but you will try to use the adjacency matrix when your number of vertex is very large. That is, you have a dense graph. And if you have a sparse graph, right, where your number of vertex is very less, then you start using this, because this matrix will be an overkill. It will take some space. This is the space that it takes. V square, of course. This side V, this side V, total number is V square in terms of space complexity. This is where I said we will derive. Now, remember the concept of summation of total degrees is equal to 2 times the h. Summation of total degrees is 2 times the h. That is what formula we had learned. There is only one formula, handshaking theorem. Summation of total degrees is 2 times the total number of edges. Now, summation of total degrees. Now, what is the total degrees in a complete graph? Now, complete graph is where every vertex connects to every other vertex. Now, what does that mean? That means that if I take a graph like this, every vertex is connected to every other vertex, right? So in this case, how many edges will this particular person have? This particular, if this is a person, then how many edges will it have? Or let's say vertex, how many edges it will have? 2. 1 here, 1 here. So it will have 2 edges. If I say that this is my new graph, then this person now has 3 edges. This person now has 3 edges, right? So this person now has 3 edges means that I have made the number of vertex as what? 4. But that means every node therefore has 3, which is n minus 1. What is 4? N is the total number of vertex is 4. Then what are my edges? The edge is going to be for a particular vertex. Let's say this is A. Then the edge of A is going to have, what is the number of edges that is there, right? Number of edges that is there for A. How much is that? 3. What is the correlation? EA is equal to n minus 1. Then EB will also be equal to n minus 1. So if this is B and I draw it like this, then EB will also be equal to n minus 1 because EB also has 3. Then EC will also be equal to n minus 1 and ED will also be equal to n minus 1. These are the total edges that are there on that particular vertex. Right? So the sum of the degrees is what? What are the total edges? Total edges is nothing but degree. So then the sum of the degrees of all the 4 vertex is what? N minus 1 plus n minus 1 plus n minus 1 plus n minus 1, because I have 4 edges, right? So if n minus 1, n minus 1, n minus 1, n minus 1 are my 4 edges degrees. Degrees is total number of edges, right? So total number of edges, here we have proved that they are n minus 1. So this is the total number of degrees. Then don't you think this should be equal to 2e? This is the formula I am applying. This should be equal to 2e. So total number of edges n minus 1, n minus 1, n minus 1, n minus 1 means what? N into n minus 1. 4 times n minus 1. 4 is what? N. So n into n minus 1 is equal to 2e. That means this is what is coming. E is equal to n into n minus 1 divided by 2. This is what is coming out of it. So every vertex, if it is connected to other vertex, then the total number of edges is n into n minus 1 divided by 2. So you see this, if every vertex is connected here, every vertex is connected to every other vertex. Total number of edges is how much? Total number of edges is 1, 2, 3, 4, 5, 6, 6 edges. And what is the vertex? 4. That is n. N is 4. So if n is 4, then 4 into 3 divided by 2 is this 12 divided by 2, 6. And that is your total number of edges. So this formula holds good. So that's the formula for calculating this particular kind of sums that may come. Paths and circles easy. Path is like this. Circle, this is a path, right? Path, we have already seen path in trees. Same thing, same concepts. The total number of edges is the path length. The length is the total number of edges. Cycle, we have talked about it, that you will revisit back the node where you started from. That is what is the cycle. Now comes graph traversal. This is where we'll spend some time. We have around 20 minutes. We'll spend some time here. Let me go back to the chat window. Camera off. Yeah, we are back. Who is saying what? Let's see. Ghost Coder says, if you don't mind, can you tell me what's the difference in graph that we have in DSA and the discrete maths? Graph in DSA and discrete maths. It's not going to be anything different. If you go to MTech, there is a paper called Advanced Mathematics. So there you will see that you will be studying the same graph, the same thing that we are studying here. So it's not going to be anything different that you are studying there versus here. A graph in mathematics is the same thing as, obviously there will be a lot of mathematical formulas, but a graph is a graph. It will have a vertex, it will have an edge. There will be relations between them. F has degree 2. I don't know which F here, so I'm sorry, I can't answer that. B has an out degree 2 and F has an in degree 2. 2 is greater, 2 is going to 3, 4 is a directed graph then. Which example, Ketchup Night? 2 going to 3, 4. 2 going to 3, 4. It's not going to, if you see. This you are talking about. Yeah. That way you are right. If this says going to, then yes, this is a directed graph. That way you are right. Exists at 1, 1 and 2, 2. Then the vertex will have a loop in it. If an element exists at 1, 1 or 2, 2. Yes, there is a loop. If you have a 1 here, if you have a 1 here, then there is a loop between at this point. You will have a loop here. According to adjacency matrix. Okay, done. Okay, so this is all. I will go back again. Let's continue. We start with BFS DFS now. So be concentrated here, because you are asked to solve or do a BFS or a DFS given a particular graph. Get to a BFS DFS of that particular graph. So I'm trying to explain that to you, how to do a depth first or a breadth first traversal. Now 1 minute, let me see where this is. Yeah, got it. Okay. I hope you are seeing this. Let me see what you are seeing. Yes, you are seeing it. We are trying to do a breadth first search now. What is breadth first search? It goes by levels. This is one level, this is one level, this is one level, this is one level. So breadth first search is called level order search. It is done using queue. We will see how it is done using queues. Right? So we will visit here, then we will go here and complete this, then we will go here, complete this, then we will go here, complete this. So that is how we will go. But then to do that, we will have to use a queue. And for that, let's see what are the. So I will write the steps now. Just have a look at how we are trying to solve it. We'll keep the graph on this side, and we will write the steps on this side. Okay, I hope it is visible. I need a lot of space, so I'm just trying to create some space for me. Yeah, so let's start off. Now remove A first, because that is the node, and we will take it out and print it, because we have in fact what we have to do first is a queue has to be created. So a queue will be created in step 1. A queue will be created, and inside that queue we will keep A. So inside the queue we will keep A, because A is the root node, and I will maintain a visited set. In that I will keep A, because I have taken A, I have visited A, right? And then my current output is nothing. Output means the breadth first search output of the number of, or the sequence of the nodes is what was expected out of it. We have to create a sequence of what will be printed if you do a breadth first search. So this is my first step. My second step is that we will remove A from the queue, because there are because A is the only person in that particular level. We will now pop A out of the queue. As soon as we pop A out of the queue, we have the liberty to take it in the output. So in our output, we will say that we have taken A. Right? So we have taken A, that means it comes as an output. And in the queue, what we will do is, we have now moved to the next level, and in the queue, therefore, in the next level, we have B and C. We will push this into the queue. So my visited sequence now looks like A, B, C. Right? So this is how we are moving on. Next, we will remove B from the queue, because queue we will pop means this element will come out, right? Because we are not finished with this level. So we have to pop out that B. As soon as we pop out something, it goes to the output. So A, B will be my output, right? So we have to pop out that, and when we pop out that, we will also need to investigate. We will also need to say that okay, one more 1 minute. Let me see if I've done this correctly. Visited. Actually, did I take C? Okay, yeah, good. So my queue, when I remove this particular element B from the queue, looks like that because I have taken out B, my Q actually will now look like D and E will get added. Why? Because as soon as you pop out something, I missed to tell you this, as soon as you pop out something, your job is also to push its children into the queue. So you are popping out B, so push the children into the queue and take that pop out into the output. So you are popping out this B, right? So you are popping out this B means B is the first element in the queue. So you are going to pop out that. So then I have C as my first element. C becomes my first element. So C becomes my first element means that D and E will be entering into the queue because B has gone out. So B's children is D and E. So D and E will now come into the queue. So what are we trying to create? We are trying to create, see, these are the levels, and we are now gone into the second level. So at every level we have to take all the elements into the queue one by one. That is what we are trying to do. So my output is AB for now, and so we have CDE. So our visited set now becomes A, B, C, D, E. This is our visited set. A, B, C, D, E. Output is A, B. Now we will remove C from the queue. So we will remove C from the queue, and when we remove C from the queue, our output will become A, B, C, and the queue will therefore have let's say so when we remove C from the queue, does C have any children? Let us see. C has a children in F, right? So you'll have to add F into the queue. So your queue will have D, E, F. As I said, if you remove something from the queue, insert the children of that into the queue. That's what we are doing. We removed C from the queue, so we will insert the children into the queue, which is F. C's children is F. So the visited node will now look like A, B, C, D, E, F. Right? So that is what my visited node will look like. Now we will remove D. The next element is D. So we will remove D from the queue. So we are now going to remove D. So my queue will look like what we will see. But if you think about it, the queue will not change, because once you remove this D, there are no children of D. So you cannot add anything in the queue. So it will remain as E and F. Output will be A, B, C, D. Right? And the vertex, visited vertex will be, let me see what are the visited vertex. The visited vertex will still remain as A, B, C, D, E, F. That is what it will be. A, B, C, D, E, F. So that is on this side. Now E and F is there, so we will remove E from the queue, and when we remove E from the queue, my output will be A, B, C, D, E, because I have removed E, and now I have to check whether E has children. E has children, which is G, so I have to put it inside the queue. So the queue will be F and then the children G. Right? So the queue now has F and G. My visited is going to have G additional now. So my visited will be A, B, C, D, E, F, G. Now the seventh thing when we will do is that the queue we will take out F. Now F does not have any children. So then if F does not have any children, then I will keep this as G. And my output therefore becomes A, B, C, D, E, F. And my vertex becomes, or visited vertex becomes A, B, C, D, E, F, G. Nothing changes on that visited part. So now if I remove F, which we have already done, so we have to remove G. So when we remove G, then we have G doesn't have any children, so nothing gets pushed into the queue. So the queue becomes empty because G doesn't have any children. So the output therefore becomes, because we popped out that particular element, A, B, C, D, E, F, G, which means all my vertices have been visited also. Sorry, I took a mistake here probably. A, B, C, D, E, F, yeah, G. A, B, C, D, E, F, G. And I have my output as that, and my visited nodes will not change, it will remain the same. There are no fresh visits I am making. So A, B, C, D, E, F, G will be my visited nodes, and this will be my final output because my queue has become empty. Right? So I hope you understood how we will do this, and this is how the queue is getting used. So all the while we will pop the element out and add the children there. Whenever it is popped out, it goes to the output. That's the only funda that is available here. Let me go to your chat window and see if you understood this. I went again, is it? Camera on. But the camera looks visible. Guys, can you see me? Is it an old chat? Just confirm you can see me and then we can move on. Okay. Okay, so I hope you have understood then breadth first search, how we did it. Let's move into depth first search. Same thing we will take in depth first search. Depth first search, there is one key concept which we call as backtracking. So if there is a short question which says in which search we have backtracking, please use that we have backtracking in depth first search. In which sort we have level order, in level order is in breadth first search. Queue based is breadth first search. Backtracking is depth first search. Stack based is depth first search. So those are the 2-3 differences. Differences also come, and these are the differences that you need to talk about. In depth first search, what we typically do is we will typically move like this, and once we don't get anything, we will start backtracking. We will come like this. Once we don't get anything, we'll come back. We'll go like this. Once we don't get anything, we'll come back. If everything is visited, our job is done. So that is what we do in depth first search. So let us do a depth first search in the same manner that we did just now. Okay, so from A we will go to B, right? So from A we will go to B. That means my stack which started with A, so we'll start the stack with A first of all. Let's do that stepwise. Step 1, my stack will be having A, right? So stack has A, and in this stack my visited is A, and my output is A. Because I am visiting, I will take it out as an output. In the earlier case, you were putting it inside the queue, and when you are popping it, you are taking it as the output. Here, when you are visiting it, you will take it as the output. Now from A, where all can we go? We can go here, we can go here, right? So we will take the first child of A, that is the left child of A. So that's where our second step will be that B is our first child of A, so that will go inside my stack. So my stack now will have A and B, and my visited nodes will be AB. So this will be a set, so AB, and my output will be another set which is going to be A to B, or whatever way you want to write it, comma you can also use. So that's my output that we are trying to see, because as I said, output, you will take the output as soon as you visit it. That is why you put it in the stack, means you have visited it, you will take it in the output. Now from B you can go, you have to see how you can go. From B, if you see here, From B I can go to D, and from B I can go to E. So I will take the left child. So I will say stack A, B, D. This is what I will say. So stack A, B, D is what I will say. Now visited will be A, B, D, and my output, because I took D, my output will also have D. My fourth step, after D, where can I go? After D, I cannot go anywhere. Now I will backtrack. This is where the backtracking comes. Now backtracking will return it to B, and in B we have D already visited and E not visited. So when I backtrack from here, I'll come to my parent, and I will see from B where all I could have gone and which I have not gone yet. I have not gone to E because I took the left child and went from B. So I will have not gone to E, I will go to E. So if I go to E, then my stack will contain A, B, D, E, and my vertex therefore will become visited. Constantly I am taking this as vertex, I don't know why. A, B, D, E, this is my visited, and my output, because I took E, will become A, B, D, E. That is going to be my output. Now from E, where will I go? From E I can go to G because that's the only child. So I will go to, my stack will increase from A, B, D, E to G. So G will get added, and the vertex, the visited will be A, B, D, E, G, and my output will be A, B, D, E, G. I will take G because I have added it to the stack. Anything I added to the stack as far as depth first search is concerned should go immediately to the output. Right? So next, add G, I have nothing to do because I am now at G and I cannot do anything. So I have to backtrack. When I come to E, I see that E also has nothing to give me because E is completely empty. Similarly, if I go to B now and backtrack to B also I have completed these two. So nothing to do. So I will go to A. I see that C I have not done. So this will go into the stack. So stack A, B, stack A, B, one minute, I made a mistake here. After so when we actually encountered a backtracking scenario, which was here after A, B, D, this D will go out of the stack. This D will go out of the stack. Why? Because we encountered A, B, D, and when A, B, D got encountered, D did not have any child. So therefore we went back. Before going back, we will pop out the D from the stack because D is not having any children. It has no relevance anymore. We have already taken it as an output, so we will take it out. Similarly, when we were here at G and we went back and we were trying to add C, right? So this D does not exist here in this stack, and our output is A, B, D, E, G, A, B, D, E, and then G comes. G comes, and A, B, E, G is my stack, which is okay. A, B, E, G is my stack. So now we will now have to go back, and we are going back, and because G had a null child, therefore G will be removed from the stack. So when we are going here, we will remove G. We will not have G here, right? So that is what we will do, and we therefore will have A, B, E, and then we will add C to it because A, B, E was already there. G has no child. G gets removed. We went to C, so C got added, right? So we have A, B, E, G. Next, we are visiting. So we have visited A, B, D, E, G. So we have visited A, B, D, E and G. Yeah. Yeah, A, B, this one we have visited. If we sort and write, then we will say that we can sort and write, we can also give C here. I'm just sorting and writing A, B, C, D, E, F, G is what we have visited, right? So we have not visited F yet, so A, B, C, D, E, G, and the output here is going to be A, B, D, E, G, C. That is what the output will be. It's just become slow again. A, B, D, E, I forgot to write E here, my bad. So A, B, D, E, G, C. So that's going to be your output. And once from C, I can go to either left or right. So I will go to the right, which is my last iteration. So we will have a stack which will say that my stack now has so E, we have A, B, E, C. Let me see what my stack will. From C I can go to F. So F will not have any children, so I will have to stop there. So what we will do is we will say that my stack here which has let me see, something is wrong in this problem. Somewhere I have made a mistake for which this confusion is coming. From A I will go to my child C, which is right, and my stack at that point in time will look like A and C. Of course yes, this is the mistake I have made. So when I'm going back, right, I have to remove the nodes. That's what I told you. When I'm going back, I have to remove the nodes. So these nodes will go away, right? So this is what I have made a mistake. So the stack will keep on getting emptier. And when I'm going up, I will have to remove this also. My stack will have to get empty. So I have to go to A, B, E. E does not exist. And then I have to go and come to F. So when I go to F, then it is also B I have to remove, because B I have covered. See, B I have backtracked, E I have backtracked. So these will all go out from here whenever I'm coming out. So this is not anymore there. So that is why now we have A and C. And A and C that we have, we are going to F now. And when we go to F now, it will be A, C and F in our stack. So our visited nodes at that point in time will be A, B, C, D, E, F, G. The same thing, A, B, C, D, E, F, G. And my OP will be A, B, D, E, G, C, F. That is because we are, whatever we are taking off, whatever we are visiting, we have to write it. A, B, D, E, G, C, F. Because that is the order in which we visited. So whatever we are visiting, we are putting into the stack. And whenever we are coming back, we are removing from the stack. So that removal part, I'm sorry that we could not do it in one flow. The removal part I had made mistakes. And when we are removing things, when we are coming back, we have to remove things from the stack. This is your final output. So might be that the removal might have to happen here or here, which I would have missed. But from this step onwards, it should be okay. In fact, this is okay, I think. But if you think there is a mistake, I hope you can correct it. What I'm trying to say is, when I'm going back and I don't have a child, I'm going back. That means that that particular node has to move out, right? It doesn't have a child. Its job is over. Its job is over. It doesn't need to stay in the stack, right? So that's what we will try to say. So that's how we will do it. Now, how does this stack become empty? This output comes at the 8th step. We will be taking. We have done with F, so we will backtrack. So we will backtrack. When we backtrack, F goes away. So the 8th step is that the stack is now A, C, because F goes away. Next, and nothing changes in the output, right? Next, C will backtrack to A, because C is backtracking, its job is over. So it will have A. And then the last step will be, the stack will become empty, because A has nothing to backtrack. So that is how the stack will become empty. So you have to make the stack empty in order to stop the program. Nothing changes from the output perspective. So that is on your depth first search. And I'm sorry that we could not do this particular area in one single flow. Yeah, so this is something that I missed out here. So I hope you are understanding that whenever we are going back, if we are going back like this job is over, so remove it from the stack. If you are going back like this job is over, remove it from the stack. This removal I missed to do in some instances, which created this confusion. But the more or less the logic is that you visit, you enter the stack, you come out, you exit the stack, and whenever you visit, you put it in the output. So that's on DFS. Let me go back and see what is the questions. You want the 7th step onwards repetition. 7th step onwards. Okay, 7th step onwards repetition is easy. Your output has already come. So now you are here, right? If you remember, we had put F. You had put F. That means you are here, right? So if you are there, then you need to now go to your children. Your children doesn't exist, so you will backtrack. So when you backtrack, your job is over. So you will remove yourself from the stack. You are no more in the stack. So your stack contains AC. No fresh person comes in because you did not have any children. If you had children, that person would have come in, right? And you would have also stayed in the stack. You will only go out of the stack when you are doing a backtrack, and you will enter the stack when you are doing an inside, when you are visiting it. So you are now here. Here you are seeing that all the children are covered because your visited is saying that everybody is covered. So now you will backtrack again, right? So when you backtrack, your job of C is over. So remove C from the stack, and that's where you get an empty node after the last step, where at A you also have nothing to do. So you are going to exit the program. There is no backtrack, but exit the program. That means again job of A is over. That means take out A. So your stack becomes empty. As soon as the stack becomes empty, print this output. This is your answer. So Tanmoy, I explained the 7th step. For 6th step, does the stack consist of only AC? For the 6th step, yes, for the 6th step, the stack consists of AC because you have backtracked, and therefore all of this are out of your stack. So you have come to C means what? AC means what? AC means you have come to C, right? That means all of this side is covered, right? Your job for all of this is covered except for A, whose right child you are still doing. Everything else is covered here. That means you would have backtracked all the nodes. They should have been exiting by now. They should not be in the part of the stack. So that is the 6th step. Srijit. 7th step I have done. Transition between 6th and 7th. C will also be visited. In the 6th step, C will also be visited, Srijit. Right? So because you have visited the 6th step. In the 6th step, you have entered into C. So C will also be visited. So that's why I put C here. You may not put C in between. You can sort the visited, because visited is for you to probably refer. Is there anything left? So if you sort it and keep it, it becomes easier to refer. Right? You may not do sorting here. So that is on this particular side. Srijit, C is on right is okay, but in the 6th step I have already entered C here, which means I have visited it. Why is there a confusion? I am here, na? It is on right and I am already here. I am at here. In the 6th step, I am already at C. If I am at C, I have visited C, and therefore that visit should enter me into my visit array. Okay, so I hope this is clear. Now I will give you an assignment between your lunchtime and whatever you have, or even at the day end you can give me. I will give you a particular graph for which you do a BFS and DFS. I have kept this here intentionally. Yeah, so please note this graph. I already have a solution here, but don't, in fact the solution might be wrong. Don't look at the solution. Yeah, this one. Please take a picture of this and come back to me with a solution. Please post your solution as a camera picture of your copy in WhatsApp. As a camera picture of your solution in WhatsApp. Find the BFS and DFS. Okay, start from 1. Starting node is 1. Take a picture of the screen and work on this whenever you get some time. Work on it today at least, because you learnt it today. You should work on it today. And post that answer in WhatsApp. Let me see how many of you do this correctly. You will go to your GPTs and Geminis of the world. You will get various different answers. Okay, don't get confused. We have clear-cut rules discussed today. Please rewind, understand what is that, and do according to that. That is the only rule. Don't go to your Gemini and GPT. Of course, it may give the right answer, I don't know. But definitely if 10 people ask it, it will give at least 3 different answers. That I can assure you. Okay, so that is on this assignment. Which data structure is primarily used for breadth first search? Q. A 3 regular graph has 10 vertices. How many edges does it have? A 3 regular graph has 10 vertices. That means a 3-degree graph. A 3-degree graph has 10 vertices. Total degree is how many? 30. Right? So total degree is 30, means 30 divided by 2 will be my total number of edges. Why? Because I know that my total number of degree is equal to 2 times the number of edge. So 3 times 10 vertex is 2 times edge. So 30 divided by 2 is the total number of edge. So I told you, right, that's the only formula in this entire chapter. This is the only formula, and questions will come around this formula. It will be addition, subtraction, division, multiplication. Only that will be there. You have to be intelligent enough to do it. Convert the following adjacency list to an adjacency matrix. I hope all of you can do it. See, A goes to B and C. So A will go to B and C. B will go to C. C will go to A. Right, so we can now, that's your adjacency matrix. Very simple. This is one more on BFS, but then BFS I think you can do. BFS is much more easier and we have explained it. So I will not explain this here. Is the following graph connected? The following graph are not connected because you don't have a connected means every node there should be one edge connecting that node to another node. That is what is connected. So there should be something like this, or there should be something like this. So 4 and 5 are never visited. So if we start visiting here using BFS or DFS, we will never be able to go to 4 and 5, which means they are disjoint. That is how the computer figures out whether it is connected or disconnected. It will do a BFS or DFS and say that I cannot reach 4, 5. So I do not agree that 1, 2, 3 and 4, 5 are one single graph. Find a valid topological sort. Topological sort means my in degree here is 0, and my out degree here is 2. Here my in degree is 1, out degree is 1, in degree is 1, out degree is 1. So wherever my in degree is the lowest will be the starting point, and wherever my out degree is the highest will be my ending point of the graph. So the topological sort means that from a topological perspective, if I sort this, where will be the first node, where will be the last node. So that can only happen in a directed graph and through in degree and out degree. So that is the answer to this. Does this graph contain a cycle? Of course this graph contains a cycle, because whenever we come back to A, starting from A, if I go like this, I will definitely come back to A. So if I come back to my originating point, then this is a circle. Tree versus graph we have explained in the beginning of the problem itself. So that's on graphs. So now we will start off with this thing, our what is that? Heap, right? We'll start off with heap, but let's do a quiz first. Okay, be ready. Let's start off. Chalo, graph starting. '84. Let's start off. Gitika, Shayan, Bhavya, 62% accurate. 9 of you answered degree. The answer was already mistyped in choice D. You never noticed that. That's why I was laughing. I had mistyped the answer in choice D. Okay, so number of vertices is the right answer. Number of vertices is the order of the graph. And number of edges is the degree of that particular vertex. Good. Leaderboard, Shayon again at the top. I don't know what magic he does. Nice, very good. V into V minus 1 by 2. Arindam Mundol, okay. Very good, guys. You're listening. Good, 85. 2 into E is the answer. Nothing changes on the leaderboard. Let's move on. Let's see how many of you get this correct. What happened? 52 only. There was a minus sign in between. So n minus 1 is the answer. V minus 1, 1 minus 1. N minus 1 is the answer, guys. We discussed this also, but that's okay. Might be getting confused. I'm ending the quiz. Priyanshu good, Ayush good. Tanmoy, I'm seeing you first time on the leader. Good. Okay, so let's move on. Yeah, where are we? Here, okay. So we start off with heap. So the first thing that you need to remember is heap is a complete binary tree. When we say complete binary tree, if you remember from what we discussed earlier, a complete binary tree is what? A complete binary tree is a tree where all the levels are full except the leaf level. That means all the levels are full means that if you have, we had discussed, right, level 0 will have 1 node, level 1 will have 2 node, level 2 will have 4 node, level 3 will have 8 node, level 4 will have 16 nodes. So if we have so many nodes, then, and if we are actually at this level, then this should be filled up. That is, 1 node should be already there, 2 nodes should be there, 4 nodes should be there, 8 nodes should be there, and in this we can have a partial fill up of this particular 16 nodes. So that's what you see here. Here in this level 2, this is level 1 and this is level 0. So in this level we should be having how many nodes? We should be having 4 nodes. Do we have 4 nodes? We don't have 4 nodes allowed, because this is the leaf level. Right, so that's what you need to understand from a complete binary perspective. And you also have to remember that all the levels will be filled up from left to right in that sequence. I cannot create a tree and claim that it is a complete binary tree if it is like this. You will argue probably that this is a leaf level. Why are you forcing me to keep 4 nodes? I'm not forcing you to keep 4 nodes. I'm saying that this node should have come here, because you are supposed to fill up from left to right. So those are the 2 properties that you have to remember. Right, so complete binary tree which has completely filled, and the last level has to be filled up left to right. Now that is basically all you know, right? You all know that the shape of this tree should be a complete binary tree, and a complete binary tree is this. We have discussed it yesterday. But the heap order property, there is a special property of this complete binary tree. It says that whatever nodes or whatever elements you have on this side, each of the parent should be greater than the children, any children, and for a heap which is classified of type max heap. So there are 2 types of heaps. One is a max heap, one is a mean heap. So if it is a max heap, we are talking max heap here. This is a max heap. So this max heap actually has each of the parent is greater than any of the children. It is not like binary search tree. Left side should be less, right side should be more. No, all of them should be less. All of them should be less than 25. If I take this particular parent, then all of this should be less than 18. I hope you are understanding the difference between BST and max heap in terms of the requirement. So if it is a max heap, then you have the parent should be greater than children. If it is a mean heap, you have the parent should be less than the children. So that is the only difference between max and mean heap. So if you see this, then of course I hope you can understand that this is the problem I told you. Heap is not a binary search tree, and the reason I already told you. But what is the height of this tree? The height of this tree is the total number of levels, right? And the total number of levels we have already explained many a times. So again, I'll probably do it. At the 0th level, we can have 1 node. At the 1th level, we can have 2 nodes. At the 2th level, we can have 4 nodes. At the 4th level, at the 3rd level, we can have 8 nodes, and I can write 1 as 2 to the power 0. So what I'm saying is this 0 I'm trying to correlate here, right? So that is what I'm trying to do. At 2 I can say 2 to the power 1, here I can say 2 to the power 2, here I can say 2 to the power 3. Therefore at the kth level I can say it is 2 to the power k. What is 2 to the power k? 2 to the power k is going to be your total number of nodes, right? So the total number of nodes will be 2 to the power k, and k is what? K is your height. Number of levels is also the height, right? So the height of the tree is also k. So k is your total height. So if k equal to not 2 to the power, k equal to 2 to the power k, so your total number of nodes that you will have will be that this log base 2 of k, which is equal to your total number. So 2 to the power k will be equal to, at some point 2 to the power k will be equal to your n, which is your total number of nodes. So the total number of nodes here will be equal to, if I take log on both sides, k will be equal to log base 2 of n. So that is how we will calculate this So what I'm saying is 2 to the power 3, 2 to the power 2, all these are total number of nodes. So I will get 2 to the power k as the total number of nodes, which will be equal to n, right? So this n is my total number of nodes. So what is the correlation then between height and n? So k is my height. Why k is your height? Because k was the level number. Is level number my height? Of course level number is your height. Check it out, level number will be your height. So 2 to the power k will be equal to n, and take log on both sides, we will get that. So we have explained this in 2-3 times in the last 2-3 days. I just thought that if you have missed that, then we'll complete that. Now we'll talk about what the max heap looks like here. If you see the max heap here, if I take these elements, by the way, remember that when you are given to create a max heap, you will actually create it in the sequence that is given to you. So this is the sequence in which you will go in order to create the tree. Do not do any other sequence, right? So we will see how to create it. For now, assume that this, if we would have taken a max heap out of it, then this is how the heap will look. See that every element below this parent, every element below this parent is less than 91. And take any node and see the descendants. You will see everybody is less than that parent. That is the property of a max heap. If you don't do that, you have not created a max heap. So max heap is complete binary tree that we have already seen, that which is greater than the left child as well as the right child. Both the cases we have to satisfy. That's the difference between your binary search tree. And always remember that the root of a max tree will be the maximum element of this max tree. Always it will be the maximum element, and this is the property we will use to do a heap sort. So we will do heap sort today, and that's where we will see how heap sort is done. Because we are doing heap, I thought we will complete heap sort. Will not keep it pending. The largest element is at the root, and if you had understood yesterday, or I think day before, rather yesterday I think, that how to convert this graphical structure into an array so that we can store this tree in an array. How did we do that? We said that we will go level by level, right? So we said we will go like this. We said we'll go like this and put 91. Then we said we'll go like this and put 73 and 88. Then we said we go like this and put 54. And then we said 54, etc., etc., whatever the number, and the last record also goes here. So if you remember that, then for a particular child index, I'm putting this up on the chat window. For a particular child, and this is index based, means one index base, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So for a particular child which is at 88 or which is at the index number 3, what is the formula to get to the parent? What is the formula to get to the parent of I equal to 3? Chat window. Ketchup night, not 3x2 floor. Typo. Good. So you remember from yesterday. So to get to the parent, I have to do I/2 floor. So if I do 3/2 floor, then I will reach 1.5 floor, and that will mean 1. So if I go to 1 index, I will see the parent. 88's parent is 91. Yes, 88's parent is 91. So that is why we taught in trees how to store it in a array, because now max heap we will be utilizing this concept. So that is max heap. Min heap is just the ulta. So the minimum element will be at the top. So the minimum element is always the root in a min heap, right? And the array will be the way we will create the array in this particular statement is, I think the array is created wrongly here. Yeah, it is a copy paste error. So the array will also have to be created ulta, right? So do not see this. I will change this in the PPT. This is a typo. This is wrong. because as you understand, you will have to go from left to right, top to bottom to create the array. So go to left to right means 6 will have to come first here, right? Then 10, 15, then 37, 42, 29, 88, 91, 54, 73. That's not what this shows. So don't get confused with this. I hope you understand. I hope you acknowledge. Next, we will talk about if a heap is already given, how do we insert an element into that heap? So 92 is supposed to be inserted into that heap that we saw earlier. What is this heap? This heap is a max heap, right? So I want to insert 92. So let's see how we insert. Insertion will always happen at the leaf, right? So insertion will happen here, right? Now I want to insert here. Is it allowed? Yes or no? If not, why not? I want to insert 92 here. Will it be allowed? Give me the reason. All no is fine, but give me the reason. 92 will go to the top. That I'm not questioning. You are not getting. Dev Malyo has answered it correctly. Farhan, I didn't probably phrase the question correctly. Child less than equal to parent. All that is fine. I have not even gone there. I am asking between 92 here and 92 here, which one should I use? Which one should I use? That's my question. Yes, the left one. That is what I was asking. Why the left one? Because we have to do a left to right. Because we have to do the left to right. Yes, it has to be a complete binary. It's not a binary search tree, Farhan. Complete binary tree. Who said complete binary search tree? Okay, so now let's move on. We will insert it here. We can't insert it here because we are not allowed. We have to insert left to right because it's a complete binary tree. Now, if we insert it here, problem with that is that once we insert it here, we have to see that it does not deviate from the condition of the tree. Just like we did in AVL, we have to keep on balancing the inserts. Here also we'll have to keep on balancing. Right? So what we'll do is, we'll say that my 92 that we have inserted here, it should be greater than the parent. Sorry, 92 should be 92's parent should be greater than itself. So 29 should be greater than 92, but that's not the case. So how do I understand from my array? So my array says that 92 is supposed to be inserted here. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 37. So an 11th element gets created with 92. So this is my array. Right? So, and I told you that the parent of a particular element is what? I is equal to 11. Then my parent is at I by 2. The floor of that. So the floor of 11 by 2 is 5.5, which will give me 5. So at 5, I will find I should be getting 6. Something wrong I did. Aha, my bad. All of you did not catch it, is it? Let me see the window. Yeah, nobody caught it. This is because the space is so small here. I was thinking that the next left is under 29. The next left is not under 29. It is to the right of 42. Isn't it? It is to the right of 42. So I want to insert 92 here. Why didn't you guys catch it? Eye problem. Okay, good. My eye problem also. So now I have 5 here calculated from 92. So if I go to 5, I will see 42 is its parent. Right? So 42 is greater, should be greater. 42 is not greater. Then do a swap. So we will do a swap here. So when we do a swap, the tree, let me start drawing the tree because I can't change in this side. So I will change in this side. So I will say 91, 73, 54, 42, 88, 29, 15, 37, 6, 10, 92. And we will just join them. Right, and that's what we will have. Now in this, what we will say is that 92 will be swapped. So if 92 is swapped, then let us do that. So 42 will go away and 92 will come up. So 92 comes up here, 42 goes away. Now 92 still has to be greater, or 73 has to be greater than 92, because 92's parent is 73. This is a max heap. The parent has to be greater. So 92's parent is not greater, na? 73 is not greater. Do a swap again. So do a swap again means, let us see what we do. We will say 73 here will be swapped with 92 here. So then we will say 92 here, 73 here. Now what is 92's parent? 91. That still is smaller. So we will have to do a swap here. And all this while you are using your I by 2 concept to get to your parent. I am not repeating that. I hope you understand, because this is graphical. You are not going to do this graphically. You are going to do I by 2 concept to get to your parent and understand whether a swap is needed, and then do a swap on the array. So then we will now say this will go here and this will go here. So we will have 92 here and 91 here. So this is how you will do a heap insertion, right? So we will, every point in time, once we insert, it should satisfy with its immediate parent. If it satisfies, heap insertion is done. If it doesn't, go on till it satisfies. So that's what heap insertion is about. Now how many times did I have to do this, or how many maximum times will I have to do it? Don't you think that whatever I did is the maximum time? I inserted something here and I had to go all the way up here by checking once here, once here, once here, right? What is that? That is log base 2 of n, because the height of the tree is log base 2 of n. So if you are here, that is the worst case you can actually do to get to the top. So to get to the top, you'll have to convert, go the height. The height we have already proved just now that it is log base 2 of n. Right? So that is what is the complexity of heap insertion as far as a heap is concerned. If insertion is possible, deletion is also possible, and deletion is where the important nature of the tree will lie. So listen out carefully. If this is the tree, and what this is the same tree that we have used earlier, nothing changes. Deletion of a heap is always from the root. Deletion of a heap is always from the, like in a stack you are not allowed to go inside. Similarly, heap also you are not allowed to go inside for deletion. You are allowed to go inside for insertion, but not for deletion. You'll always have to delete 91. So when is 91? 91 is here. So when we have to delete this, let me draw this now. 91, 73, 54, 6, 10, 42, 37. 91 will go to 88, 29, 15. Right? So this is what your heap will look like initially I am supposed to delete this. So when I delete this, my last element will replace it. Right? So my last element is at the index number 10. So through my array, I know what is my last element, and I also know what is my first element. So I will put 37 here, and this space will become empty. This space will become empty because I have deleted 91. I don't need to keep it. But in case I need to keep it, I will understand that my array has been split here, because the deletion will logically change the size of the array by one element. So I have changed logically the size of the element array by one element, and I am just storing whatever I deleted here. I am just storing whatever I deleted here. This is not a part of the array because it is already there as a space. I am trying to use it, that if I need this deleted element later on. So 37 will go to the first, just like what happened here, and the 91 will be stored at the end, but it is beyond the array. So 37 instead of so this element will become empty. This area will become empty, and we will have 37 going to the top. Now you start figuring out whether you have a proper heap or not. 37 should be greater than 73 and 88. It's not. So if it is not, then you will have to take the maximum element and actually swap it with that. Out of the two childs, whichever is maximum, out of these two childs, whichever is maximum, swap it with that. So 37 will be swapped with 88. So this now becomes So this now becomes 88. And this now becomes 37. Right? Now 37, you are working with 37, right? So 37 has to be in the right place. So 37 is greater than 29 and 15. Yes, stop. So that is how you will do deletion. Now this tree is a proper heap. This tree is a proper max heap. Check it out. You have deleted 37 and 37 is not here. Sorry, not you have deleted 91. My bad. You are supposed to delete only the root element. 91 is not there in this tree, and the way we adjusted this tree made sure that now 88 is the largest element, and that 88 has moved to the top. That is why we had taken the largest element to the top. One of the properties of a max heap is that the largest element of the tree will be at the top. So we were at the root, right? And the largest element has to be at the root. That's why we took the largest element of the two children. So don't worry about that. Your thumb rule is, whenever you are seeing yourself as disbalanced, the children will come up and help you, but the oldest children will come up and help you. That way you have to remember. So my largest element will come up and I will move down. Right? So that is what this heap deletion tries to tell you. So that's on this. Again, here also you never know till what point you have to go to adjust. So the worst case will be the height of the tree, which is log base 2 of n. So now we will build a heap slowly. Right? So we talked about an existing heap, how we attacked that existing heap by inserting an element, how we deleted an existing heap how we deleted an element from an existing heap. But how to create the heap, that is what we will talk about now. Before that, let me see if there are any questions. Okay, everybody has gone to an eye doctor. That is okay. Let me continue. So this is my 10, 20, 15, 5, 30, 25. Now this 10, 20, 15, 5, 30, 25, I told you have to take it in sequence. So add 10 first. Add 10 first and see what happens to the next element. So add 20. As I told you have to add from the left. Add 20, you have a problem. Swap it. You have a problem, swap it, because you are asked to do a max heap. I don't think they have asked anything. Assume a max heap here. If they don't, then just assume something and write that I have assumed max heap and I am doing it. 20, 10. Right? So this is now okay. So next, what we will do is we will say that okay, 20, 10 now looks like I have to add 15. So I have 20, I have 10, I will add 15. Next, from here I will add 5, 10, 15. This 5 I will add to the left of this. It is in the right place? Yes, because 10 is greater than 5. Next, we have 30 to be added. So 20, 10, 20, 10, 5, 15, 20, 10, 5, 15, and we were talking about what? Adding 30. Okay, 30. So 30 added. 30 added does not work for us. So we will swap it like this. So when it swaps, it becomes like this: 20, 30, 15, 5, 20, 30, 15, 5, 10. So that is what it will be. Now 30, you're not safe because you have made a swap. That swap should hold good for all levels. 30 doesn't hold good for all levels, so you have to make a swap here. So this becomes 30, 20, 15, 5, 10. Right, so that's what it will be. Next, you have 25. So 25 will come here. 25 is not in the right place, so we will have to make a swap here. So we will do it as 30, 20, 25, 5, 10, 15. Right, so this is our answer. We have got the same answer. So that's how you will do a max heap building. What is the complexity? Complexity is again log n, but every element that you place, every element that you take could be log n. So when you place 20 first, you could have taken order of 1 complexity. When you take 10, right, this 10 could have given you 2 swaps, or one. Basically you would have to have moved that 10 to the top, which is from level 1 to level 0, right? So you have to move that. Similarly, 15 could have actually moved also, in case 15 was not 15, and then this 5 could have moved. This 30 has definitely moved. So how many? Every element is risking how much time? It is risking log n time. Every element. So each element might take, worst case it might take log n time. Each element placement. How many elements are there? N elements. So every element takes log n, n elements takes n log n. Therefore time complexity is n log n. So that is how you will do it. Building the heap. I will take a pause. We'll go back and see if there are any questions. I don't see any questions. That is fine. Move on. Okay. Now the same heap that we have built, we will try to sort it. Right? How do we get a sorted output from that heap? Now that we have built a heap, the most important utility of a heap is getting back a sorted output. Like the most important utility of BST is getting back a sorted output. Similarly, here also for heap, getting back a sorted output. So there, what we'll have to consider is that this is our heap that we have built. So if we have built this heap, what we'll do is we will start deletion. We will start deletion one by one. Right? So let us take this array. The same array that we have for this is 30, 20, 25, 5, 10, 15. So this is the array representing this heap. Right? Now what we will do is we will delete this deletion happens from the top, right? So we will delete it. So when we delete it, this goes and stays outside the array. Now because we are deleting, my array size has reduced. So now outside the array means this 15 will no more be here. This 15 will no more be here. This 15 would have moved outside, inside here, because we are going to take the last element and put it here, and we are going to take out this element and kill it. Instead of killing it, we are putting it in this wasted space. We are putting it in the wasted space. Now what we will do is, we will say that this 15 has gone here. So my array, my heap looks like this: 15, 20, 25, 5, 10, 15. This is how my array looks like. Sorry, heap looks like. So in this case, my first thing is this 15 should not be there, because this is something that we are pushing up, and this place gets free, right? So this place is being utilized here for just a temporary storage. That's why this element is no more there, because we have deleted this tree. Now if 15 has moved up, let us balance this. 15 is not supposed to be here, so there will be a swap between 15 and who? 20 or 25? 25 is the largest, so we will swap it with 25. So it will be 25, 20, 15, 5, 10. Next we will be deleting. Now this is balanced. Next we will again delete. So this will delete. So if this deletes, then what will happen? So by the way, now our array would have also changed like this, because for this swap our array would have changed like this. So we would have had what? We would have had 25 here, and 15 here. So 25 here, 15 here, right? And then we would have, that's how this would have looked. And then we are taking off this 25. We are deleting this 25. If we are deleting this 25, then see this array. When we are deleting an array, this particular element, what will come? The last element. The last element will be swapped. So this space becomes empty. So this space becomes empty. So in this space, what will be put? We will put 25. So we are putting 25 here, and we are putting 10 here. 10 goes up. Why this space, empty space, we are putting 25? Just from a future standpoint. Just from a future standpoint. So what we will do is, we will say our array has now become like this. So this is only our valid portion of the array, and we have pushed 25 there. So in this way, what will happen is that the next time we will delete 25, 10 will come up, which means it will look like this: 10, 20, 15, 5. So this is the array it will look like. 10 has gone up. See, 10 is going up, and this position is discarded, right? So we will have this. Now what we will have? 10 is not in the right place. Who will come? 20. So we will swap 20. So we will now have 20, 10, 15, 5. So 10 and 20 will be swapped. So let us do that. 10 and 20. I'm not erasing anymore. I'll just write 20 here, and I'll write 10 here. Right? So 10 and 20 are getting erased, getting swapped. Now we have, the next time it comes here, what will happen? Next time it comes here, and by the way, what has happened here on this side of the world, what has happened is this space got free, and in this space, what did we keep? We kept 10. We kept 20, because we had swapped. We have not. We have not done the deletion. Okay, now we are going to do it. So this 20 that is at the top now can be deleted. So when we do that 20 deletion, because 20 is at the top, who will swap it? 15 will swap it. And this therefore now becomes, this 5 will now go to the top. Right, so this 5 will go to the top, and therefore this space now will become free. So this space now will be occupied by 20. So this space is now occupied by 20. Right, so 20 now occupies that wasted space. So now you have moved 5 to the top, means you are now here. So 5 is here, 10 is here, 15 is here, and this node is broken. So that's what you have. And then you have to rationalize that. When you do that, then 15 goes to the top, 10 comes here, 5 comes here. Right, so that is what your node, your present thing will look like, which means that you will have 15 here, you will have 10 here, and you will have 5 here. So these are not there anymore. 15, 10 and 5. Now when you see this is balanced. That means you can now start the deletion. When you start the deletion, then this particular 5 will move here. Right, so the 5 will move here. When 5 moves here, then the new tree will become like this, 5 here, and then 15 has come here. Right, so instead of 5 here, which is a wasted space, what do we have here? We have 15. So here we have 15 because 15 has been deleted, na? So we will take it into that wasted space. So now we have 5 here, and 5 has moved up, 15 is out, and then we have 10. That 5, 10 is not balanced, so we will balance it out. So now what do we have here? We have like this. So this is 15, this is 5, this is 10. Yeah. So what do we have here? We have 10, we have 5, and we have 15. Now our next step is 10 and 15. So 10 will be deleted. If 10 is deleted, then we will create a space for holding 10. Right? 10 is deleted means 10 comes here, 5 goes here. So our new array, our new graph will look like this. Our new graph will look like this, which is 5. Because after that 10 has got deleted, na? So that node becomes empty. So we only have 5 now. So we will delete 5 and use the same logic. So 5 will stay here. Our row will move like this. So the entire array now, which was a wasted space, now contains all the deleted elements. And you can see that all these deleted elements are now in a sorted order. 5, 10, 15, 20, 25, 30. That is why we were storing it in the wasted portion, so that ultimately when everything gets deleted from the heap, the entire array gets filled up with a sorted structure of whatever data you had. So that is how we will build a particular heap sort. So the heap creation, we said we will take order of n log n. Each delete will be log n. We see that because we have to do the heap5 process again. Therefore, order of log n plus order of n log n will be the highest that we will take, which is n log n. So the overall heap sort total is order of n log n. So that is your complexity of the heap sort. The heap5 process, which is something that we have already done. We have 20 more minutes. Let me see if we can do an example. Let's do an example. Let's do this. Okay, and I'll come back to all the questions. We'll discuss all the questions, don't worry. Only thing that I'm skipping is the heapify process, which we have already done, but it will be a different thing. So what I'm skipping, I'll tell you. What I'm skipping just for the lack of time is this entire thing of building the heap. This entire thing of building the heap took n log n. This process is called as heapify. Now this heapify is through the insertion process. Right, so this process is by insertion, that we are inserting a node every time we are getting it. So this takes n log n. However, there is a heapify process which takes less than n log n, and that is called as heapify through leaf non-leaf insertion. So heapify through non-leaf adjustment. Sorry, heapify through non-leaf adjustment. This is something that I will probably park it, not that important, but the important part is that this again is taken from the last slide. This is not applicable here because we are not deleting anything here. We are just talking about creating the heap, right? So the creation of the heap, heapify through the non-leaf adjustment. When we do it through the method that I'm talking about here, which I am unfortunately not covering now, is going to give you an order of n complexity for inserting the elements or creating the heap. So creation of heap can be done through two ways. One, through insertion, and two, through non-leaf adjustment. And this non-leaf adjustment is an order of n. This is n log n. And this creation process is called as heapify. We have seen this. We are parking this. We will see if we can see this also. But what I wanted to solve is some questions. Okay, we will solve this shorter ones and then we will come back to the longer ones. The time complexity of heap sort in the worst case. Time complexity of heap sort in the worst case will be n log n, because we have seen it here that heap sort total takes n log n, right? So that is why we will say the time complexity is n log n when a sorting technique is called stable. A stable sorting technique, please focus your attentions here. If we have an input like this, after stable sorting, now this is not related to heap sort only, it can be any sort. Suppose you have the list of elements like this, then after sorting it will look like 2D, 3B, 5A, 5C. Now if you see, the sorting happened through the numbers. So 2 came first, 3 came first, next. Then why did 5A come first? Why not 5C? Why not 5C? Both are 5. So why not 5C? Because 5A appeared first here. 5C appeared second here. So whatever is your appearance order will be also your sort order. If that is the case, then it is called a stable sort. I hope you understand. I'll repeat again. If there are elements which are like this, 5, 6, 9, 5, 6, 9, 1, 7, 5, and I want to sort it, my sorting will be, suppose this 5 also has, to recognize this 5, I will recognize this 5 with a different color. So now we will sort it 1, 6, then we will say 5, then we will say this 5, then we will say 6, sorry, my bad, then we will say 6, and 6 will not be here, no, doesn't come up at all. Yeah, so 5, 6, 1, 5, 5, 6, and then we will have 9, 7 and 9. So this is what is a stable sort. The position of your duplicate element is maintained in the result, and that's why it is called a stable sort. If it is not the case, then it will be a unstable sort. So which are stable sorting algorithm? all your bubble, insertion, merge are stable sort, whereas not stable sort are your heap, quick sort and selection sort. So heap that we are learning today is actually a unstable sort. It does not actually care because it anyway has to move around those thing to the top, right? So where it comes, it doesn't care. It cannot guarantee that it will be in the same order. So dash is not a stable sorting algorithm. Heap sort is not a stable sorting algorithm. Time complexity of heap sort in the worst case we have done. So this is repeated. Okay, this is repeated. We have completed this. Now we'll do this question. The max heap represented by an array constructed from a list of numbers. So we will now construct this max heap. It's going to be simple, right? So let's do it. 30. Then we push 10. Then we keep 80, which means the swapping will happen. So then this becomes this. Then we will make it 60. So 80, 10, 30, 60. Swapping will happen. 80, 60, 30, 10. So that swapping happened. Then we will make 15, 80, 60, 30, 15. So 15 will go here, which is okay. Then we have to have 55 come in. So 80. So 55 will go where? 55 will go here. Right, so 55 will go here. Which is not sorted. So we'll say 80, 60, 10. 15 will lay wherever it is. And then we will have 55 go to the top because of the swap, and 30 will come this side. Then we are getting, now this is okay. Then we are getting 17. So we will insert 17 and this is perfectly fine. So that is the answer to this question. I hope you understood how we approached it. Now let's do this. Let us do this also. Then it will complete the, this will be the last one. So this will complete it. So let us do this. Draw the minimum heap from the list. So if we have 12, then we will have 11, then we will have 7, then we will have 3. So far so good. Then we will have 10. So far so good. Minus 5. So this minus 5 is now creating a problem. So what we will have is minus 5 will move from here to 7, and from 7 it will move to the top of 12. So minus 5 will move all the way to the top. I'm just writing it directly. There will be 2 swaps. I just wrote it directly. So minus 5 will go to the top. 11 will be here. 3 will be here. 15 will be here. What is this? 15 or 10. Okay, 10. Then we will have 5 has moved to the top. So when 5 moved to the top, 7 had moved down. So it is actually replacing 12. So 12 will come here, and then 7 is here. Right? So what are we doing here? We are, I forgot to say, or I don't know whether you noticed, we are doing a minimum heap. Actually, that is something that I also didn't notice. So I thought that, I remembered that we had to do the minus at the top. So from a minimum heap perspective, we will have to revisit this. Right? So this is not a minimum heap creation. So we'll have to revisit this. Quickly, let us do it. We will take 12. So be careful, like you don't make mistakes like me. I'm getting old, you are not. So 12 comes here. 11 is a minimum heap, right? So 11 should move to the top. So this will mean that we have 11 and 12. Then we have to put 7. So 7 has to go to the top, which means that it will become 7. If I put 7 here, 7 has to go to the top. That means 11 will go to the right. Right? So this is how it will look like. So I am doing the swap in one shot. Then we will have 3. Now 3 will go where? 3 goes here. If 3 goes here, is it okay? No, 3 has to go right to the top. So 3 goes here, then 3 would have swapped 12, so 12 would have moved out, then 7 is here, and then 12 is here, and then 11 is here. So that is also 3 done. Then we have 10. So 10 will go where? 10 will go here. Is it okay? Yes, it is okay. Minus 5. Minus 5 comes here. Is it okay? Of course not, it is not okay. So this minus 5 will go all the way up. So this will become minus 5. And then we have 7 this side. We have 12. We have 10. And on this side, this minus 5 would have replaced 11. So we have 3 here. So 11 is this side. And then we have 0. 0 comes this side. So 0 comes this side means we will have to swap it with 3. So we have minus 5, 7, 12, 10, and then 0 has come up. So this is 0, and then 3 is on the right of 0, and 11 is anyway here. Then you have 9. So 9 can be inserted here. So 9, if it is inserted here, it is not right. It has to be swapped with 12. So this becomes minus 5, 7, 9, 12. And then we will have 10. And then we have 0 here, 11 here, and 3 here. Now it is okay. Now what we have left is 2. So we will insert 2 here. And the 2 is okay? Yes, the 2 is okay. So this is your answer. Now, if we actually do the deletion, then minus 5 will come out. So minus 5 has come out as my first element. What will go up? My 12 will go up. This will go up. 2 will go up. So 2, how will it go up? 2 will go up like this. From here, it will, in fact, we will replace it directly, and then we will see whether it is not getting adjusted, then we will adjust it. So we will say that 2 is here, 7 is here, then 10 is here, then 9 is here, 12 is here. What did I make mistake? Acha, 7 said 10 is here. 2 will have 0. This is actually a 0. And we have 11 here. And we have 3 here. So this is after you move out 5. Now in this way, we will, now is my 2 in the right place? 2 is in the right place. Because 2 is not in the right place because 0 is here. So we'll have to adjust 2. We'll have to bring this down and 0 will move up. So that becomes this tree. So this will be 0, which will move up. This will be 7. This will be 2. Then this will be 9. This will be 10. And this will be 12. And this 2 will be from here. The 2 has 11 here and 3 here. So this is how I moved up the element. I got out minus 5. This is the deletion, the same deletion that is happening in the last slide I showed you. The same concept is being shown here. Now, I will not do the rest. I'll assume that you can do it because this will take another 5-7 minutes if I attempt to do it. Every element at the top I will be removing. Right? So, if you see the next element that will be removed will be this element. What is this element? 0. So, do you think you are getting a sorted order? Yes, minus 5, 0, etc. etc. So, those way it will come out. So if 0 moves, 12 will go up because it is the last element. Now 12 will have to adjust. Once we adjust, something will come to the top. Then we will delete that. This way it will go on. So I hope you understand. Let me see the chat window. What is going on? Yes, so that is something that I missed to tell you. If you do a min heap sort, then you are getting an ascending order. And you can see that is what is coming out. We did a min heap and we are getting an ascending order. Farhan, you had a question. Vice versa for max heap. Farhan, you had a question. Sir, can you show the deletion in the second last tree? Element gets deleted, 17 goes on the top. Second last tree, second last tree, second last tree. This one. Is this what you are talking about, Farhan? Okay, so where are we saying that you have a problem? 30, 10, 80. Okay, this is a max heap. Then there is no deletion happening, Farhan, here. We are just creating the heap here. Why are you saying deletion is happening? Can you show deletion in the second last tree? Because when the element gets deleted, Acha, you are asking that if we delete, then what will happen? Is that what you are asking, Farhan? Okay, good. So second last means this. I'm assuming this is what you are considering. So here Farhan is asking, suppose we are deleting this heap, then what will happen? Right, so we are deleting this means that we are taking away this element out. So this element comes out of the tree. So then what happens? 55 will move up. Okay, so 55 will move up. So if we move 55 up, then is 55 sorted? That's something we'll have to check. So we will delete this and then we will make this 55. The system has become slow again. Okay, so we'll delete this and this will be 55. Come on. And this node does not exist, right? So 55 has moved up. Now when 55 moves up, is it in the right place? No. 55 when moves up, it is not in the right place because 60 is there, which is greater. So this 60 will go up, 55 will come down, 30 will go right, 10 will go left, and 15 will go here. Now 60 is in the right place. So that's the deletion, Farhan. I don't know whether this is what you wanted. क्या हो गया? अच्छा, you want it on the final one. So you said second last, though I thought it is this. So you want it here. Okay, we'll do it here. Don't worry. So this is not this that we wanted. Okay, you want to delete 80. You want to delete 80, then 17 will go to the top. Right, so 17 will go to the top. So 17, 60, 55, 10, 15, and then we have 30, and this is the problem. As soon as I take this, it slows off. Yeah, the machine is also asking us to take a break. Yeah, okay, so we'll finish off in 5 minutes. So 10, 15, and then we have here, what did we have? 17 has gone up, 30 comes down. This is what we have. So 80 is out. Now 17, will be swapped with 60. So 60 moves up. So we will have 60, then we will have 17, then we will have 55, then we will have 10, then we will have 15, then we will have 30. Now 17 is right place. Yes, 17 is in the right place because we have 10 below it, 15 below it. So this becomes your next tree after deleting 17 from that, after deleting 80 from that particular tree. So 80 has come out, 70 got adjusted. Farhan? Okay. Mr. Farhan, please confirm. We are getting into the quiz. Okay, chalo, quiz. Come on, quickly. How many of you are here? A lot of you would have broken off for lunch, I guess. 85, okay, still good. Let's start. %72 খিদে পেয়েছে বোঝা যাচ্ছে, because this was an easy thing, na? It's a complete binary tree, that's all. It was clearly called out. Good. 78. Nothing. I don't see new names in the leaderboard. Purnima Kumari, okay, new name. Sorry, Poonam Kumari, new name, good. Arunima Paul, new name, I guess. But then what happened? It's not n log n. N log n is when you are inserting the entire tree. The time complexity of heap insertion, okay, it's an ambiguous question actually, if you ask me. So one element will take log base 2 of n. N elements will take n log base 2 of n. So either way this C or D could be interpreted. So I think between 41 and 39 both of you are correct. So I will see if I can give marks to both of you. That's on this. Let's see a 100% score. I never saw a 100% score. Arunima Poonam Upasana 67. What happened? Heap deletion is always from the root, guys. It's not the leaf. Leaf is for insertion. Come on. Good. Okay, so let's see the score. Alim Ghazi, Upasana, Arunima. Okay, good. Arunima, I think I'm seeing you first time on the leaderboard here, at least in top 1. I don't know where Shayon went. Good. Okay, guys, so since we are breaking at almost 10 past 1, we will connect back at 15 past 2. Right, so 2:15 we will connect back. 2 o'clock the link will be published. I'm closing this live session just because I'll need to restart my machine to get it back. That's my machine's lunch. Right, so we'll get a new link at 2 o'clock. We'll meet you at 2:15. Chalo, thank you.